All right, I'm going to present some work coming out of the collaboration formerly known as IHESP, the International Laboratory for High Resolution Earth System Prediction. I'd like to acknowledge that this was very much a team effort, so I want to give credit to all of these co-authors: Ping Chang, Gokhan Donabasoglu, Nan Rosenblum, Fred Castruccio, Chuying Zhang, Abhishek Gopal, and Cameron Rankurl, who all played a part in the results that I'm going to share with you today. The funding for this work came from our Chinese partners, Qingdao National Laboratory for Marine Science and Technology, and the computing resources came from TAC, the Texas Advanced Computing Center. So I'm going to start out just with kind of some broad background on the state of the science in decadal climate prediction, highlighting two of Doug Smith's works to just give you a flavor of where things stand in decadal prediction. So the Decadal Climate Prediction Project, which started circa CMIP-5, is an experimental protocol that allows for large multi-model ensemble analysis. And that has enabled us to look at skill in initialized prediction with very large ensembles. So in Doug's 2019 paper, he combined 8 prediction systems, giving a ensemble size of initialized hindcast that was order 71, and he compared that to an ensemble of 56 uninitialized projection runs. And the main takeaway from this paper is that for near-term 5 to 10-year climate outlooks, initialized decadal prediction ensembles exhibit robust skill improvements over uninitialized projection ensembles. So what you're seeing here plotted is the forecast year 2 through 9 anomaly correlation coefficient spanning roughly this time period. You see on the left the total skill for temperature, precipitation, and pressure. A lot of high skill, certainly for temperature. Noteworthy regional skill for precipitation and pressure. And then on the right-hand side is the impact of initialization. So clearly much of this skill is coming from the external forcing, but this paper shows quite clearly that initialization enhances the prediction skill over and above what you get with just external forcing. And then in 2020, Doug followed that up with an even larger analysis that combined CMIP-5 and CMIP-6 prediction ensembles, giving an ensemble size of about 170. And the conclusion of this paper is that, consistent with findings from seasonal prediction, signal variance is too low in decadal prediction systems. And by signal here, I mean the forecast ensemble average, which corresponds to the response to forcings plus any predictable internal variability. And so the upshot is that very large ensembles are needed to achieve skill for atmospheric variability, and that's now widely known as the signal-to-noise paradox in initialized climate prediction. To explain the plots, I'm going to just go through some common skill metrics that not everyone may be familiar with. First, the anomaly correlation coefficient should be familiar. It ranges between -1 and 1. It measures the ability of the forecast ensemble mean to predict the phase of observed variability. And here, n in this expression is the number of time samples. So for decadal predictions, we're generally dealing with 40 to 60 time samples. And what you can see on the upper right here is the correlation for forecast year 2 through 9 winter sea level pressure. With this grand ensemble that he compiled, we see quite high skill scores over much of the globe. And it's considerably higher than if you subsample that ensemble and look at 10-member skill. So that increase in ensemble size is key to achieving this high skill for winter sea level pressure. The mean score skill score ranges between minus infinity and 1 being a perfect score, and this measures the magnitude of forecast error variance relative to observed variance. So in the upper right, you can see the mean square skill score for DJFM sea level pressure showing positive values in many of the regions that show high correlation score, but also some regions of negative skill. And then the UK Met Office has introduced this idea of the ratio of predictable components. This is a metric that ranges between 0 and infinity. It measures the discrepancy between the signal to total variance fraction in forecasts and that from observations. So what this is the ratio of the correlation coefficient that you achieve with a prediction system divided by the signal to total variance ratio of your prediction ensemble. And for perfect prediction system, we expect this ratio to be 1, but the signal to noise paradox corresponds to RPC being much greater than 1, implying that real world predictability is higher than model predictability. And there have been many studies looking into this issue. Here you can see the map of RPC for winter sea level pressure showing values much greater than 1, where this high skill in the North Atlantic is achieved, suggesting that the model is deficient in its representation of signal. You need these extremely large ensembles to see any skill in this quantity. So we've been involved in this decadal prediction game for a while now. We submitted the CESM decadal prediction large ensemble to the CMIP6 DCPP effort. This prediction system had initialized ensemble size of 40 that was paired with an uninitialized ensemble of 40. And we showed that there's quite high skill in the North Atlantic. Here I'm showing detrended SST correlations. And we also were able to then show that there's significant skill improvement over our uninitialized projection runs, particularly in the North Atlantic, but also in other regions, as you can see here. And the DPLE was the first system to demonstrate high decadal predictability of winter NAO, with skill steadily increasing with ensemble size. So we found high skill for a forecast year 2 through 8 ensemble average of winter NAO. And the ACC didn't saturate. As you can see, it looks like it would still increase with an even larger ensemble. And the RPC for this particular quantity in DPLE was about 5. So another point of evidence of the signal to noise paradox in our own system. So the motivating questions for the high resolution work are: how does decadal prediction system performance change with model horizontal resolution? Does resolving mesoscale air-sea interactions help to address the signal to noise paradox in initialized climate prediction? And what are the predictability limits for regional scale climate extremes on multi-year to decadal timescales? I'm not going to be able to cover all of these in this talk, and I'll really mainly focus on an answer to the first question and offer some tentative answers to this second question. So let me introduce the high resolution decadal prediction experiment that we conducted in IHEST. We call it HRDP, and I want to contrast it with our previous effort, DPLE. The reds here indicate important differences from the earlier effort. So we used a slightly updated version of the model, and if you're interested in the differences, you can refer to Chang et al. The main difference, and the one that we're going to focus on, is the change in horizontal resolution. So we moved POP from 1 degree to 10th degree. We changed CAM from 1 degree to 1/4 degree, also moving to the spectral element version of CAM. CLM then inherits the CAM grid, and SICE4 inherits the POP grid. There are some changes in initialization. Both of these efforts used FOSSE to initialize the ocean and ice. That's a forced ocean sea ice simulation. But for HRDP, we're using a high-res FOSSE now, and we're forcing it with OMIP2 forcing, which is a JRA GOGO-DO product. We initialized the atmosphere in HRDP straight from the JRA 55 reanalysis. And then we also made an effort to initialize land in this new system. So we're using an AMIP run forced with observed SST to initialize the land component. Now, there's a big difference in in the hindcasts between these two, we were able to achieve 18 start dates for high resolution. So we're nowhere near the 64 start dates that we had in DPLE. And we could only run these for 5 years due to compute constraints rather than a full 10 years. And finally, ensemble size. We're using a 10-member ensemble in high-res DP, 40-member in DPLE. And so the net compute resources entailed running 930 years of fully coupled high-resolution CESM compared to 26,000 years of fully coupled standard resolution CESM. So before I get into the HRDP results, I wanted to spend some time talking about this high-resolution FOSSI. So apart from the external forcing, the initialization of the ocean component is thought to be a key source of prediction skill on decadal timescales. So we spent a lot of effort scrutinizing and trying to improve our simulation of historical variability in the ocean at high resolution. So I'm going to compare the high resolution FOSSI to a low resolution counterpart. Both of these have been run over 4 cycles of OMIP2 forcing, and I'm going to particularly focus on North Atlantic dynamics here. Here's a comparison of the AMOC stream function in depth space, the contours of the mean stream function, the shading shows the interannual standard deviation after detrending. And some things to point out here. First of all, AMOC strength at high latitudes in high resolution is somewhat weaker than low resolution. So on the right here, I'm looking at 2 latitudes. The blue curves show the AMOC strength, red curves show the meridional heat transport. So AMOC is slightly weaker at high latitudes, slightly stronger at lower latitudes in high resolution. However, the meridional heat transport is higher at both latitudes. So we're still transporting as much or more heat in high resolution. Furthermore, I want to point out these small numbers, which maybe you can't see. These are the correlations over each cycle between the AMOC strength and the heat transport. So you can see these correlations are above 0.9 at low latitudes. So AMOC is really explaining most of the variance in heat transport at these subtropical latitudes. But at higher latitudes, AMOC in depth space is not explaining even more than half the variance. So these are correlations of roughly 0.6. We're explaining about 40% of the variance. I also want to point out the low AMOC drift and robust forced variability even in high res. So we're pleased when we ran these that our AMOC drift is quite low compared to the internal variability that's forced by the Jairy-Gogo forcing. And we can also see evidence of kind of similar forced variability. So we have this spin up of AMOC followed by a decline. And we see that both in low res and high resolution. So it's more pertinent to be looking at AMOC in sigma space if you're really interested in the heat transport and the predictability of heat transport in the high latitude North Atlantic. So now I'm showing you the similar plot as before, but now AMOC in density space. We can see similar structure of variability in high res and low res, these lobes of high variance in the deep western boundary current and North Atlantic current, both of these simulations. If we compare the time series now, we see that, again, the heat transport is the same as before, but now we have slightly stronger overturning in density space at high latitudes and high resolution. And now we can see these correlations explaining more than 80% of the heat transport variance at this sort of southern boundary of the subpolar gyre of the Atlantic. So this nice match between the low res and high res force simulations suggests that both exhibit hallmarks of Labrador seawater driven coupling of the deep western boundary current and North Atlantic current that explains the high North Atlantic scale in our coarse resolution prediction system. So this gives us confidence that the mechanism at work in DPLE will also be at work in our high resolution DP system. I just wanted to throw this in, which shows the robust forced variance in AMOC at high latitudes. This is showing cycles 1 through 3 from low resolution and then 1 through 4 from high resolution. And we see this, this high signal to noise of Atlantic thermohaline circulation in high res, which wasn't obvious when we started this, that the eddying ocean would show this robust response to forcing as we repeat cycle after cycle. But in fact, we find that the eddies are not introducing too much noise in this kind of key pillar of prediction in the North Atlantic. I also want to point out the high signal to noise in SSH. So large-scale extratropical SSH variability is a key element in North Atlantic decadal predictability. And this goes back to studies by Griffiths and Bryan in '97, who showed this dynamic topography, EOF, in their perfect model predictability experiments that I've shown is also at play in the high scale in our DPLE system. So here the contours are SSH anomalies. You can see this SSH dipole over the mid-Atlantic ridge that's very much reminiscent of the earlier Griffiths and Bryan study. When we look at SSH in the high-res FOSSI and we do a correlation of cycle after cycle, we see very low forced signal in the Gulf Stream extension region. So there's a lot of eddy noise here that makes it quite different from low res, where that forced variability gives you very high correlations throughout the North Atlantic. But if you look at the large scale, so if you look at an east-west SSH gradient between these two big boxes, this increase in that gradient is what contributed to the mid-90s warming that is highly predictable in decadal prediction systems. And we see a same high signal to noise in that east-west SSH gradient in high res. So high res FOSSI appears to be fit for purpose for initializing high res DP. However, this is a result that gave us some pause before we started the prediction experiments. When we look at the reproduction of observed SST and upper ocean heat content in the subpolar North Atlantic in this box, we get a very good correspondence in low res with observed benchmarks. So the observations are dashed here, and I'm showing cycle 1 through 4. The correspondence is less good in high resolution. We get this early warming in the late 80s rather than the mid 90s, both in SST and upper ocean heat content. So this is something to keep in mind, that we haven't exactly nailed the high-res FOSSI simulation to give us high confidence that we have a good reproduction of observed variability in the North Atlantic. All right, I have some time remaining to show you high-res DP results, but I might skip this slide and just jump to the global skill maps that I want to show. So here I'm looking at pentadal average surface air temperature from high-res DP and DPLE. You can see that skill is quite high in both of these systems, and the skill patterns are a very good match. And so clearly external forcing is contributing significantly to much of this high skill. If we want to answer the question, is high-res DP doing better than DPLE, we have to control for ensemble size. So we resample DPLE across member space to build a distribution of 10-member DPLE hindcast scores, and then we can compare a 10-member HRDP to 10-member DPLE. And now I'm showing you a map that shows where we have 90% confidence that high-res DP is better than DPLE, and then filled circles show where it's likely worse. So apart from this region in the North Atlantic and maybe the Indian Ocean, high-res DP is showing mostly better skill over much of the globe than DPLE adjusted for ensemble size. And we can also look then at mean square skill score, so testing for improvements in forecast anomaly magnitude. And we also find that high-res DP is generating better anomaly magnitudes over most of the globe. And there are exceptions, certainly from region to region. Briefly, precipitation. Here I'm looking at annual mean pentadal average precipitation over the globe. The take-home message is that high-res DP has higher skill than DPLE over much of the globe, although here there's more exceptions. So clearly a lot of regions where we see a degradation in skill with the high resolution. What I want to end with is this analysis of winter sea level pressure. So here, again, I'm looking at skill on a 5x5 grid. My verification data set is ERA5. And what you can see, if we compare the 10-member DPLE correlation score to 10-member high-res DP, a dramatic increase in correlation scores in high-res DP with significantly better skill over most of the globe. And we see the same improvement in mean square skill score. Now, SLP skill is quite sensitive to ensemble size. So if you compare the DPLE 40-member skill to the DPLE 10-member skill, you can see this impact of increasing the ensemble size and enhancing sea level pressure skill. So to get kind of skill in sea level pressure commensurate with high-res DP skill, we need a 40-member ensemble with a coarse resolution system. And so we can look at the RPC value for these two systems. Here's the RPC for 10-member high-res DP showing 1 over much of the globe where we see high skill. And this is in stark contrast to DPLE, where high sea level pressure skill is always corresponding to RPC values much greater than 1. So to conclude, IHESP has completed a set of initialized decadal climate prediction hindcasts at unprecedented high horizontal resolution. We've completed a first set of hindcasts, 18 start years, 5-year simulations, 10 members, and that's enough to permit critical drift correction needed for skill assessment over this time period, 82 to 2021. We've submitted a compute proposal to further expand the set. I show that the high-res FOSSE used for initializing ocean at sea ice exhibits low-frequency North Atlantic variability consistent with earlier low-resolution studies, indicating that a late 20th century thermohaline circulation variability and predictability mechanism is largely robust to resolution. The high-res FOSSE mismatches with observed North Atlantic variability remain under investigation. This is the main result. High-res yields significantly higher skill than DPLE after adjusting for ensemble size, for pentadal climate variability over much of the globe for surface climate fields. And in many, but not all regions, the high atmospheric skill is achieved in HRDP with RPC values near 1. And this stands in contrast to DPLE, where high ACC is always corresponding to RPC much greater than 1. This implies that increased horizontal resolution could help alleviate the signal-to-noise paradox identified in seasonal to decadal prediction studies. I'll stop there. Sorry for going over.
Thanks, Steve. We have time for maybe a couple quick questions. Let me ask one from the chat from Nikki, who can't get on live at the moment. The Southern Ocean seems to stand out as a region with improved skill in HRDP. Can you comment on why that might be?
No, I can't. But if I go back to the Smith et al. Study, Southern Ocean really stood out there as well. So I don't have an explanation for why skill is so high in the Southern Ocean, but you see that high skill even with the 10-member subsampled ensemble for sea level pressure. So this requires further investigation. What exactly is the mechanism giving this high Southern Ocean skill?
Okay. Maybe time for one more right now, and we'll defer some others till a break. Let's go with Steve Griffey's.
Steve, thanks for the talk. I didn't hear, maybe you said it, with the increased resolution in both the atmosphere and the ocean, in your concluding slide, you said that helps. Do you have a sense for whether the ocean's more important or the atmosphere is more important in that improved predictability?
I don't know the answer to that. I think, the hypothesis is that the better representation of mesoscale air-sea interaction, which requires high resolution in both components, is the key here. And I think the answer is both.
Yeah. Great, thanks.
Okay, for others who have their hands up, you can either put a question in the chat, or we'll come back for some questions when we break at 11:25. You can talk to Steve then. So let's move on to Lucas Lorindo.
Just a second. Okay, can you see the correct?
You're good.
Okay. Hi, everyone. The title of my presentation is Role of Ocean and Transferability in Scale-Dependent Earth Interactions. I did this research during my postdoc at NCAR and IHASP, and I want to acknowledge Justin Small, my supervisor, and all our co-authors in this study. I'll start with a figure from Kurtman et al. 2012 that show correlations between SST and the turbulent heat fluxes and between the SST tendency and the heat fluxes. These are from a low-res CESM simulation with the ocean and atmosphere both configured to a 1-degree resolution. And these relationships can be used to infer if the local variability is driven mostly by the oceanic or atmospheric dynamics. In A, positive values indicate that the ocean currents generate SST variability that in turn drives a response in the heat fluxes, while in B, negative values indicate that the atmosphere forces SST fluctuations via the heat fluxes. And in the case of the low-res model, we can see that negative correlations dominate almost everywhere except in the tropical Pacific and the subpolar North Atlantic. This suggests that the atmosphere controls the variability in most of the ocean. But the picture changes if we use a high-resolution ramp. Now, panel A shows strong positive correlations at regions with strong additivity, while B now shows very weak or zero values in the same regions. And this suggests that at strong current systems, ocean dynamics dominate the variability, although the atmosphere is still dominant at the interior of the basins. More recently, papers by Drs. Stu Bishop and Justin Small showed that these relationships depend strongly on the spatial scale that you're looking at. Here I try to show this dependence using data filtered in space. And these are results for a high resolution run produced by IHASP. So in panel B, I remove variability with scales that are smaller than 10 degrees. And when you do so, the correlation dropped to almost zero in most locations, and we end up with a map that's similar to that produced by a low-res model. In contrast, in C, I removed variability at scales larger than 10 degrees, and we now obtain positive correlations almost everywhere in the ocean. These are similar estimates in this slide, but for correlations between SST tendency and the heat fluxes. In B, when we remove the small scales, we now see that the values become more negative in most locations. While in C, when we instead remove the large scale variability, we end up with near zero values almost everywhere. And these results indicate that the atmosphere controls the SST and reflux variability at large scales, while the ocean processes dominate at small scales. So the main idea of this study is to investigate what are the key physical mechanisms that give rise to this state dependency. And for that, we use spectral methods to characterize the SST and heat flux variability, and also the covariability between both quantities across a wide range of spatial and temporal scales. And we also use an idealized stochastic model to interpret what is the contribution of oceanic and atmospheric processes to the observed spectrum. So I used two CESM simulations produced by IHASP. One is low resolution, LR, with 1 degree resolution in both ocean and the atmosphere. And the other is high res, HR, with 1/10 of a degree in the ocean and a quarter of a degree in the atmosphere. They are both quite long. LR has 480 years of monthly outputs, and HR has 160 years, at least the segment of data that I used. And I also used 26 years of satellite observations from the Geophoto 3 product. In this study, I compute the power spectra of SST and heat flux and the process spectra between them as a function of zonal wave number and frequency. And I calculate the spectra at each latitude of a basic mask for the Pacific Ocean that I'm showing here in this map. And to help interpret the results, I use a stochastic model for the SST evolution. This model is forced by noise terms NA and NO that represent the action of internal dynamics in the atmosphere and the ocean. And the model is composed by a turbulent influx term that encloses the atmospheric noise noise and by a radiative damping term. Essentially, I solve this model for the Fourier transforms of SST and heat flux, and then contrast the solutions with the results I obtained using CESM and satellite data. So previous studies that relied on stochastic models generally used white noise to force the solutions, but here I wanted to use noise with a realistic variance distribution in spectral space. And the idea is to check if the presence of structure in the noise can explain the scale dependence of RC interactions that I described in the beginning of the presentation. And to simulate these, I decided to define the noise using data from the CESM simulations themselves. And I chose to use 2-meter height humidity for NA because we found that it was not strongly correlated with mesoscale SST anomalies, so we thought it might predominantly reflect its variability might predominantly arise from the action of internal processes in the atmosphere. And we used ocean heat flux conversions for the ocean noise, because we know that this is the main driver on mesoscale SST variability. Essentially, I compute the Fourier transform of the signals and plug them to the analytical solutions from the stochastic model. And I then adjust the noise variance to the correct magnitudes by fitting the solutions to the SST reflux spectrum from the CESM runs. Anyway, the figure in this slide shows the power spectra of NA and NO as a function of zonal wave number and frequency. Note that they show structure. While the atmospheric noise is approximately white in frequency space, it's strongly red in wave number space, which much more power at large spatial scales. You can see that the ocean noise is a bit different. It's also red in wave number space, but it shows more variability near the dispersion relation of oceanic Rossby waves, represented here by the black lines. Okay, I'll show the results, starting with the spectra obtained as a function of zonal wave number. And these, first, the SST power spectrum, the results for the heat fluxes are visually very similar to this, so just gonna describe the SST results. Panel A show estimates for 40 south in the Pacific, where the black lines are observations, blue HR, and red is the low res results. The scale here goes from about 7,000 kilometers to 40 kilometers. Note that all data sets show similar variability over large scales, but as you go towards scales smaller than 2,500 millimeters, note that the variance remains high in observations and in HR, but just keeps diminishing in the low resolution. Panel B shows the ratio between the power in HR and LR, this time not just for the south, but as a function of latitude. The values here are in log scale, so a value of 1 indicates that the power in HR is 10 times larger than LR. And what this is showing is that these characteristics not seen just at 40 south, but occurs over most of the extratropics. And for reference, these dashed lines here represent the Rossby radius of the deformation in the atmosphere and in the ocean. Note that the largest difference between high resolution and low resolution occur at scales that are smaller than the atmospheric Rossby radius. This slide shows corresponding estimates obtained using the stochastic model, and panel A represents estimates for HR, panel B for LR, and the gray lines here shows the power spectra computed using CESM data, while the blue lines are stochastic model estimates obtained using just ocean noise, and the red using just atmospheric noise. The black lines are the sum between red and blue. In panel A, we see that atmosphere-driven component is large at large spatial scales, but its power diminishes as you go towards smaller scales. And it is this steep decrease that allow the ocean signal to become to exceed the atmosphere modulation. And note that these occurs at quite long spatial scales. In this case, about 2,500 kilometers. In panel B, you see that something similar occurs in LR, but the ocean-driven component is much weaker, while the atmosphere-driven component is about the same magnitudes and a similar shape than in LR. Now, these are the cross-spectral statistics between SST and the heat fluxes as a function of latitude, and first showing results from satellite observations. The top panel, A, shows the coherence, quantifies how SST and the heat fluxes are related with each other. If it's 0, it means that the signals are not related at all. If they are close to 1, it means that they are perfectly matched together. And the bottom panel shows the phase factor, which measures the phase relationship between both signals. And we can see two different regions here. At large scales, we see weak coherences associated with a 90-degree phase. And as you go towards smaller scales, smaller than atmospheric Rossby radius, the coherence increases while the phase goes to near 0. And this means that at this scale, both signals are positively related with each other. And now these are the results for high resolution and low resolution. You can see that the high resolution is very similar to observations. But while LR, it shows similar characteristics at large spatial scales, but much weaker coherences towards smaller scales. We can see enhanced coherences needed within the tropics at 40 south associated with smaller phase factors. So it even seems that the LR tries to do something similar than HR, but the signal is much weaker. And now these are the prospective statistics predicted by the stochastic model, trying to simulate the results for the high resolution. So here I'm showing the combined effect of both oceanic and atmospheric noise. It's very similar to what the high resolution observations are showing. And now I'm breaking down the contributions of ocean noise and atmospheric noise only. And these results confirm that this band of high coherences is coming from the ocean forcing, while the coherences characteristics at large scales are driven by the atmosphere. And now the frequency spectra. Okay, these are estimates for 40 south in the Pacific for HR. First for on SST on top, turbulent heat flux on the bottom. Again, the gray lines are the CSM results, while the blue and red lines are the stochastic model results. Start with SST. Ocean noise produces stronger variability at periods shorter than about 500 days. And as you go towards longer periods, the variability induced by the ocean atmosphere becomes more or less comparable, although here the atmosphere-driven component is stronger. In any case, you can see that both the ocean and the atmosphere produce larger SST variability at lower frequencies. So it's a red spectrum. It is well known that the atmosphere drives this kind of response via stochastic forcing, but here we find evidence that the ocean noise can do something similar. And looking at the heat fluxes, we find that the atmosphere actually controls most of the variability at high frequencies, while the ocean controls the variability at low frequencies. To double check our conclusions on the influence of ocean processes, we can also filter out the large scales. And when we do so, note that we're obtaining spectra with very similar shapes in SST and turbulent fluxes. And the stochastic model estimates indicate that the variability here is predominantly driven by ocean noise. And now, this is the coherence between SST and HF for observations, high resolution and low resolution, also for spatial scales smaller than 1,000 kilometers. Note that SST and turbulent fluxes are highly coherent in OBS and HR over the entire analyzed frequency range at the isotropics. And this is a feature that is absent in the lower S. And here, these auto panels here show the stochastic model estimates for trying to simulate represent the high resolution results. And they confirm that this can be attributed by the action of ocean noise. So the conclusions of the study, we find that the atmosphere dominates the variability at spatial scales larger than about 2,000 kilometers. And in high resolution and observations, the ocean processes start to dominate as you go towards smaller scales, and that the transition occurs because the atmosphere forcing becomes stronger as you go towards higher wave numbers, while the ocean forcing is strong. And that the transition between atmosphere-driven regime and the ocean-forced variability appears to be controlled somehow by the atmospheric Raspberry radius of the formation. It's not entirely clear why, and I think this deserves a further investigation. We also found that ocean processes can drive oscillations in SST and on the heat fluxes from the limit of the analysis of 2 months until multi-decadal time scales over much of the tropics. And finally, that the influence of ocean processes in HR is much weaker than implied by satellite and HR results. Yeah, that's all I had. Thank you very much.
Thanks, Lucas. Questions for Lucas? Bill Larch.
Yes, Lucas. Yeah, I love these kind of frequency wave number analyses, but my question is, I think the zonal wave number you use doesn't discriminate between eastward and westward propagating.
No.
And do you think you would actually see some propagating, a finer analysis that might lead to more process interpretation if you did sort it out between eastward and westward?
Yeah, for sure. I haven't done this because I don't know how to, but that's a great idea. I don't know. I talked to Justin about this some time ago, and we digged out some paper describing the code. And yeah, I think when we do this, if we plot the 2D spectrum discriminate between the propagation direction, we would see the ocean influence following the dispersion relation of Raspberry waves. And I think it's worth pursuing this type of analysis.
Okay, we have time for another question or two. Dan?
Hey, Lucas, I had a question about the kinks in spectral slope, sort of the flattening to white noise that you showed. I was wondering if you had thoughts on what controls the time scale where those sat, and also any thoughts about any injections of energy at annual scales, how that, I know that's been removed from this analysis, but how that might affect these things.
Mhm. From the stochastic model analysis, this transition between red spectrum from white spectra is controlled by the dissipation, by the damping coefficients that you prescribing into the model. So if you had a stronger damping, then this transition will occur over high frequencies. Same time, if it's weaker, would occur over longer, lower frequencies, low periods. About the injection of various annual scales, I don't know, like the model, the stochastic model, it's very simple and it cannot represent interactions, energy transfers between different scales. You know, all it does is just a transformation between the spectra and just transforms it and by putting more energy over lower frequencies. So yeah, I don't know how to. I think like to represent interaction between scales, we actually need to use like a GCM or something like that.
We're still a couple minutes ahead of schedule, so maybe I'll ask Steve Yeager if you wanted to comment on how you felt that these this mesoscale air-sea interaction process plays into the prediction, the decadal time scale prediction problem.
Yeah, so I haven't dug into the mechanisms really. I've just done the skill score assessment, but the comparison to DPLE that I showed suggested that horizontal resolution is the key difference between high-res DP and DPLE. There's some other differences in, you know, the exact methodology used for initializing and the details of the CESM model used, but you know, if the salient difference between these two systems is the horizontal resolution, then I have to conclude that it's better resolved air-sea interaction that is producing the skill differences. But we'd have to do an analysis of the sort that Lucas did to really buttress that argument.
Okay. All right. Well, thanks, Lucas. Let's move along. We have Justin Small up next. Not hearing you, Justin.
Hopefully you can hear me now. So,
Yep. Yeah.
Sorry about that. So I'm looking at eastern boundary upwelling systems.
You're still in presenter mode. There you
go. Sorry. How well is the variability in eastern boundary upwelling represented in forced ocean sea ice experiments? And this is work that was done under the IHAS project, mainly with Ping Chang, Jason Kurian, and Gaopeng Zhu from TAMU, as well as Gokhan, Steve, Fred, and Hu from CGD. Why are we looking at these upwelling systems on the eastern boundaries? They cover a small percentage of the ocean area, but produce maybe about a fifth of the fish catch. So the caveats of this study is I won't be using a BGC model or a fish model to answer Nikki's question. There's more work being done on that by Enrique and others. But hopefully the results in the physical system here are relevant to particularly a new high resolution POP sea ice marble simulations that I think Matt Long and Keith are involved in. Another reason why we do this, there's been papers initialized by Andy Bacon saying upwelling may change in the future. And caveat, that's not the subject of this talk, but Ping Chang and our group is writing a manuscript on that topic, including climate change simulations done under IHESM. Maybe talked about it in another meeting. Again, an outline and a few more caveats. I'm going to focus on the FOSI experiments that were described by Steve, which is POP2 and Sea Ice 5. We're going to start by recapping on the mean state and the biases in eastern boundary upwelling systems. And then I'll discuss the variability. I'm going to use monthly data. So I'm going to miss out some of the high frequency transient upwelling events because I'm more interested in the climate signals and longer term variability. So some of the conclusions from this study may not apply to really high frequency events. I will focus on coherent, reasonably large scale along the coast direction SST and SSH variability, because these are the variables that are best observed over a large region. So we can't do things like vertical velocity in the same way because it's limited observations. And this talk will not talk about eddy variability and energetics, which is done in a number of different studies. And the simulations, I think Steve mentioned some of this. There's two different model resolutions, high resolution, which is on the 0.1 degree grid, and the low resolution 1 degree grid. And I'll be comparing two different forcing data sets, the original core, Large and Jaeger data set, and then the evolution from JRA 55 to the Data Ocean data set for JRA 55DO, Hiroyuki Tsujino, and others, including the most recent simulation that Steve talked about, which is a high-res forced by JRA 55DO. There's some details on the parameterizations here. I will say that I think the resolved flow is most important to a lot of the things I'll be discussing here. And then a few details on the forcing data sets, for those not familiar. And I want to acknowledge these people listed here for ensuring that these runs were successful and well designed. And as an illustration of how well the model simulations do to look at upwelling in a physical space, and I'm looking here at SST in June, July, August for the California current. And the benchmark here's the observations. And you see this, the cool water near the coast. You see isotherms nearly parallel to the coast. That's the thing we want to look for of California and Oregon. If you look at these are the low resolution ocean experiments here. One forced by core, one forced by JRA 55. And if you, particularly with core, there's very little evidence of the isotherms parallel to the coast. Maybe there's a little bit down here. There's a slight improvement if you use JRA 55 with a low resolution ocean. Now, if you shift down, the bottom panels are using the high resolution ocean with core. Well, there's something there. It's not that much like observations. But with JRA forcing, you get something which I think is looking much closer to observations for this kind of upwelling patch close to the coast. And just to introduce you, the next two slides are going to be showing this in terms of bias of SST relative to observations. So here's the case for the JRA high resolution ocean minus the observed SST. And you see, well, it's slightly warm. There's a slight warm bias at the coast, slightly cool offshore. That kind of gives you a feeling of what these biases look like. And this is a good bias. It's not as bad as others, which you're about to see. So I've looked at 4 particular regions. Sometimes you can divide into 5. And on this slide, I'm comparing at the top forcing by core, and at the bottom forcing by JRA 55DO. So we're comparing the forcing data sets here, they're all for the high resolution ocean, and I show 4 regions. And what you can see is a general tendency for core of a warm bias near the coast. It's 2 or 3 degrees C commonly. California current, Peru, Chile, you see these biases along the coast. Benguela is well known, it's a problematic region. It's no exception in these model simulations. So a very large warm bias here, I've talked about that before. North Africa's Canary system is kind of a mixed bag of warm and cold biases. And when you move to the JRA 55 on the bottom, you see, well, for example, California current is improved in that the warm bias is much reduced. It's somewhat the case with Peru, Chile, although it's still quite warm off Peru. You can see here, slightly cold off Chile. Benguela, there's a slight improvement, but clearly it's still having problems. And North Africa, as I say, is a mixed bag of improvements and degradations. And now, if you look at the sensitivity to ocean resolution, which is this slide, top panels of the low resolution ocean, bottom from the high resolution ocean, you see that there are some changes. You have to look a little bit closer than for the previous slide. So the sensitivity to ocean resolution is not as large as sensitivity to forcing data set. And cut a long story short, it's mainly because of resolution of the wind structure near the coast. So for the California current, you see the warm bias in the low resolution ocean is here. These, by the way, are both forced by JRA 55DO. High resolution, you reduce that bias. It's a subtle difference for Peru, Chile, not much difference, maybe a slight reduction. For Benguela, the influence of ocean resolution is very weak. And we think that if the atmosphere forcing is still not good enough in JRA 55DO, the ocean, it won't matter what resolution the ocean is. If the atmosphere forcing has still got deficiencies, we'll still have an error. North Africa, actually there's a hint of improvement with the high resolution ocean of North Africa. It's consistently warm bias and low res, and it's mixed with high res. So I want to ask the question, how do these large biases in the mean state affect the variability in the upwelling zones? For example, I showed a case where core forcing with low resolution ocean California current, it doesn't really show much evidence of a upwelling in the mean state. How does that affect the variability? Is it much worse than other cases? And for the Benguela, well, the mean state looks awful. Is the variability unrealistic? That's the other main question. And what I'll be doing is looking at the SST, other variables averaged within 100 kilometers of the coast in certain latitude limits, and I'll show those in the previous slide. These are just showing the latitude limits for, I'm dividing into 4 cases here of California current, Peru, Chile, the kind of southern Benguela. I will be avoiding actually the worst spot of the Angola-Benguela confluence. I won't be looking at North Africa. I'll be just looking at these 4 regions. And so showing some of these results. So again, this monthly data, I've removed the monthly long-term climatology, and I've removed the trend. So I'm not looking at the climate change signal here. But what I want to point out, especially for at least 3 of these panels, each panel is a different region. It's California current, Peru, Chile, and Benguela, is actually the models which are shown in the colored symbols quite well match the observations, which is the black dots. You can see that by eye, and then the correlations, you can maybe not be able to see it, but for example, high-res J-array is 0.93. Very high correlations for SST, California current. Also high for Peru, Chile. There's hints of the core simulations, which are these blue and green, are not as good as the J-array. And then for Benguela, it's a bit more mixed. The correlations are more like between 0.5 and 0.7. Now, I thought that was good when you consider how poor the mean state is. Steve was saying correlation 0.5, not that impressive. It's not much in terms of the variance explained. But still, to me, I was surprised that they're this high. Anyway, so this is SST, but maybe that's an easy target because we're forcing these data sets with observed air temperature. So there's some constraint there. But I'd argue that's not a very strong constraint because, you know, the mean state is very poor, despite the constraint to observe TA. But anyway, we'll look at other variables, and as I mentioned earlier, SSH is the main one. Before I do that, I'm going to show influence of tropics and other modes just briefly. Again, if you look at the SST time series for California current, which looks like this, below it, I'm showing the Nino 3.4 SST anomaly or basic index. And you see it has an influence clearly on, in this case, California current. You see 97, 98 El Nino. There's a 2015-16 El Nino. But what's interesting is of California current, the warming starts before that and kind of peaks around 2014, 2015. And that's the warm blob that's very well known in the North Pacific in that period, which is believed to have a combination of remote and local drivers. So, and the correlations with Nino are around 0.5 and 6. And so ENSO has some influence on the California current, and there's papers that have looked at oceanic and atmospheric teleconnections, and also marine heat waves like warm blob have an influence. And then if you look, say, of Peru, well, really by definition, they're strongly influenced by El Nino. So if you look at the Nino regions, this is Nino 1 and 2, the eastern side for El Nino. So there's a very high correlation between the SS2 of Peru and Nino 1+2. So that's no surprise. It's interesting that actually the highest correlation is with J-array 55DO rather than core. Anyway, so I wanted to show the SSH as a variable which has more influence of deeper subsurface effects, not just SST. And what I was surprised by here is we still have a very good agreement between model and observations, again, between the colored symbols and the black dots. And the correlations are still 0.7 to 0.9, 0.93 here. The California current, for Peru, they're high. Chile, again, Benguela is slightly weaker, more like 0.5 correlation, but still somewhat surprisingly high. So I and I think others in my group are impressed by this, that despite the errors in the mean state, you still have this good performance for variability. And you can look at a few other variables. And what I've done here, I've taken the observed SSH variability as a kind of index of variability in the upwelling systems and correlated things with that index. And shown the SSH and model SSH and observed SSH. I've already shown that. Each panel here is for a different region. Let's just look at California current. Then you can look at SST and observed SSH, still high correlations. If you look at J-ray 55, HR is 0.84. Then you look at temperature 100 meters, it's still highly correlated with this index, 0.76. And 200 meters is still 0.61, reasonably high correlation. So I don't think this is this surface constraint which is driving this, but it seems to be indicating it's getting some dynamics right. Maybe the remote connections with the tropics, and maybe also local forcing and marine heat wave effects. And so this applies also to Peru, and Chile is still getting good correlations with depth. And it's definitely weaker for the Benguela. So that does stand out as kind of the least well simulated. You're getting quite low correlations. Anyway, so Benguela is still a challenge. So you can probably see and think about my discussion points. Can we use bias correction? Because we know what the bias is. We know that, and the variability is well represented. Can we just subtract the bias? In which case you could use, say, core with low resolution ocean for the California current, because the correlations are quite high. So that's a question. Secondly, what are the dynamics of the time mean bias? I didn't discuss that here. I've done that previously. There's a number of papers by our group and others. Local wind stress and wind stress curl effects are important. They have influence on Sverdrup balance and Ekman pumping and errors in those. But there's also remote influences, particularly for the Benguela from the tropical Atlantic. That's partly why it's so hard to get the Benguela right. And it's partly because the detail of the wind stress is really important for the Benguela. And then what are the dynamics of the subseasonal to interannual variability that I'm showing? This is new work to myself, that other people have been looking at that, particularly with relationship to marine heat waves and remote forcing from the tropics to the extratropics. I think they're all important, and then local wind forcing, that's likely important as well. So I'll just summarize. For the mean state bias, JRA 55DO forcing is generally much better than core. The SST sensitivity ocean resolution is less strong, but it's evident in most regions, probably except the Benguela. And ocean resolution, it is more important to fine details of SST that you probably can't see on the plot, but also to other variables, which I didn't show. The vertical velocity, which is really highlighted right in near the coast, whereas in low resolution ocean, it's weak and broad. And U and V, particularly V, has sensitivity ocean resolution. In terms of the variability, the SST and SSH variability on this kind of long coherent scale along the coast is very well captured, monthly timescales. And there's also coherence to 100-meter depth, 200-meter depth. So it's not just surface effect. And tropical forcing, marine heat waves, and local forcing, all likely important for this region. And I'll just leave it with, these are the correlations for different regions from JRA 55DO for SST and SSH being model and observations. And I'll finish there. Thank you.
Okay. Thanks, Justin. Stu Bishop has a question.
Hi, Justin. So I just pulled up Google Earth, and I was, one of the biggest differences I see between the Benguela region and the west coast of, say, South America and California is that the shelf drops off really quick, but the Benguela has a pretty wide shelf. So I'm wondering how important the bottom bathymetry might be and why the Benguela is not cooperating.
That's a good question. And I talked to Steve about one aspect of this, which is Steve has looked at the bottom pressure torque influence in the vorticity equation. And I looked at this a little bit with Steve, and I think it has some influence actually for the Canaries North Africa system, which I didn't focus on. But for the Benguela, I don't think it has an influence. So for that effect, if you look at the vorticity equation in the models, the Sverdrup balance is fairly closely holding in the model. So this bottom pressure effect is not a big effect in the Benguela. And what we believe is that in the real world, it's not necessarily in Sverdrup balance because the scales of the wind stress curl are so fine. But I don't think it's the bottom effect. I think it's more the non-linearities in the vorticity equation. Anyway, that's a good point, and as far as we've looked.
Okay.
Other questions for Justin? A quick question. I mean, this issue of trying to parse out the extent to which the atmospheric forcing is dominating the good correlation. I mean, I'm wondering, can you do something with the low res and high res coupled runs in just looking at the magnitude of the variability and upwelling in those runs where there is no such constraint? We wouldn't expect them to be correlated with one another or in any way, but there's no a priori constraint that the SST or upper ocean heat content have to follow a prescribed forcing data set.
That's a good question, and I think I didn't have time to think about the implications of these results for the couple runs, but it would be good to explore it more in the couple runs. Yes, I haven't done it yet.
Okay. Dan, Amrine?
Maybe a related question. I was wondering, if you initialized the ocean differently and ran these experiments again, could you see how differences in the ocean variability might contribute?
I think maybe what might answer this is there's been 4 cycles of the high-res FOSI, which Steve mentioned. And I did look at those briefly, and the variability is almost identical in all 4 cycles. Slightly like Steve, slightly disappointed in that, but that's what it is. So I just focused on one cycle. It's a wind force system. For what I was looking at, it had a large spatial scale. That's a wind force. If I was looking at really small spatial scales, it'd be different.
Right.
Like Frank and myself and Lucas have shown of the large scales, it's the wind forcing is and as well as the tropical forcing, but it is not the local eddies.
Okay. Final, Peter.
So, Justin, in the Benguela region, are the winds, even in the JRA analysis, not orientated along the coast?
It's really the details of the wind stress curl and the width over which the wind stress varies in the across coast direction. So the winds are in the right general direction. To answer your question, at some stage earlier in this work, I looked at things like the 2-degree atmosphere model, not 2 degrees CCSM. Sometimes the wind's in the wrong direction, but in these cases they're in the right direction, but it's really the fine detail of the gradients in the wind.
Okay, well, let's move on to the next speaker. Sanjeev Ramachandran.
Hi, let me just share my screen.
Okay, looks good.
Okay, great. First, I want to thank the organizers for giving me this slot at such short notice. So these are my collaborators at ANN, at NCAR. And I also want to thank the informal support that we all get from the X-ray and CESM community. In particular, I'm talking about Deepak Cherry and Annalena and Keith Lindsay for answering all my questions related to DAS, ConnectArray, and CESM. And the computing and analysis for these results were done at TAC at UT Austin, at HPRC at Tamu, and on Casper and Cheyenne at UConn. So just a very brief overview of some of the ocean model comparison protocols. So that was Core 1 that was initiated by Griffiths and others in 2009. So this basically entails 500-year-long simulations with forcing that repeats every 1 year. So there is no interannual variability. And that this was superseded by Code 2. And I've listed a couple of papers by Gokhan. So and the main difference between Code 2 and Code 1 was now you have interannual variability in the forcing, which now repeats every 60 years. And then you have OMIP 1, which is similar to Code 2, but with a different forcing set. Forcing set now is JRA 55. And for Code 2, it was the forcing set by Large and Jaeger 2009. And then we have OMIP 2, which is very similar to OMIP 1, but the forcing set is now JRA 55 DO as opposed to JRA 55. So the results that I'm going to be talking about today are from basically forced ocean sea ice experiments. I'll just refer to them as FOSSI, but it's very similar to OMIP 2. I want to quickly point out these are not the only 4 protocols. There are many, many other protocols. So for the results today, like I said, it's very similar to OMIP 2. The atmospheric forcing and the river runoff data is from JRA 55 DO. The ocean model is POP2. The ice model is CEIS, developed at Los Alamos. And the nominal ocean resolution is 0.1 degrees. And in the vertical, we have 62 levels. So the grid is TX.1 V3, if you care for that piece of information. So the initial temperature and salinity profiles are based on January climatology from World Ocean Atlas, and the initial velocity field is at rest. So the main goal for this simulation was basically, we didn't have a specific science question, but there isn't a high resolution POP2 data set with an active sub-mesoscale parameterization. So before we do a fully coupled simulation at high res using POP2 with the sub-mesoscale model, we thought it makes more sense to first test it in an ocean-only simulation like something like FOSSI to see whether we can get any insights. So there is an existing high-res FOSSI data set done as part of the IHES project. So in this, 5 cycles were done by people at MCAR, I believe. Each cycle is 61 years, as I said before. So that's a total of 305 years. But there is no sub-mesoscale parameterization. It was turned off. And in the 5th cycle, to reduce drift in SST, tuning of sea ice albedo and temperature under sea ice was turned on in the 5th cycle. So in the present work, what I did was I basically simulated one FOSSI cycle, or approximately one FOSSI cycle, but with the active sub-mesoscale parameterization developed by Fox-Kemper and others in 2008. So it's essentially a branch run right from the end of the 4th cycle. So that would be year 244. So we start from year 245, and we basically simulated not quite 61 years, which is the full length of a FOSSI cycle, with 54 years. So that corresponds to years 1958 to 2011. So if you use the sub-mesoscale parameterization, you have to make a choice regarding what's the value of the frontal length scale that you use. So we are just going with the frontal length scale value of 5 kilometers. The output that I'm going to be showing is mostly monthly fields. The simulation also outputted some 2D fields on a daily basis, but I'm not going to be using those. And I'm going to ignore the first 15 years to allow for any model adjustments. So the analysis uses only years 16 to 54. So this is just a quick refresher of what exactly is the sub-mesoscale parameterization. This is from the ocean modeling paper by Fox, Kemper, and others in 2011, I think. So equation 5 is basically the sub-mesoscale parameterization. It's a stream function, which depends on a constant CE that's tuned empirically. H is the mixed layer depth, and then grad B is the buoyancy gradient, F is the Coriolis parameter, and mu Z is a shape function that ensures that it's basically below, it's 0 below the mixed layer and 0 at the surface. So if you look at equation 6, you see this parameter LF in the denominator, and that is the frontal length scale I was talking about. So this is, we don't have, I should say until recently, we didn't have a very good way of trying to decide what is an optimal value, but I think there's some very recent work by Abigail Bodner and others who have come up with a model for how to prescribe LF. But in this study, we are just going with the value of 5 kilometers because that's the standard value that is used in low-res 1 degree simulations. So this is just a sanity check to show that after 4 cycles of high resolution FOSSI, the model is basically spun up. And you can see that in the values of the meridional overturning stream function. On the left is a vertical profile average between years 16 to 54, sorry, average between 2004 to 2011. So that is the last 8 years of my simulation. The red curve is from the model and the black dots are from the rapid array. So you get reasonable agreement in the top 1,000 meters. And I should point out that this is not as impressive as it looks because many models are able to generate good agreement in the top 1,000 meters. And you can see this in the plot in a recent review paper by Chang et al. In James 2020. Even the low-res models actually generate pretty good agreement with observations in the top kilometer or so. So this is more like a sanity check, and just to show that by the time you enter the 5th cycle, the ocean is reasonably spun up. And you can see that in the plot on the right as well, which shows the vertical structure as a function of latitude. And the peak values are in the top 2,000 meters or so are reasonable in what you see in lots of other modeling studies as well. So this is a plot that's comparing the mixed layer depth. So I'm calling it delta MLD, and the delta stands for the FOSSI 5th cycle with the submeso model minus FOSSI 5th cycle without the submeso. So the FOSSI no submeso is the part of the original set of 5 FOSSI cycles. So on the left is the actual difference in meters, and on the right is the value in percentage, the fractional difference normalized with the original FOSSI run. The regions in white are the places where it's not statistically significant using a 0.95% confidence interval. So if you look at the difference in mixed layer depths, the largest values I see are lesser than 50 meters. So it's not maybe that dramatic, but you see differences in the largest differences are in the Labrador Sea, and you see spots in the Southern Ocean where you see differences between 20 and 30 meters. But at 0.1 degree resolution, the change in mixed layer depth is not even, at least in this uncoupled FOSSI simulation, we are not seeing values much larger than this. And the definition of mixed layer depth, I should point out, is the one that is specified in Large et al. 1997. So it's essentially the shallowest depth where the local Brunt-Weisler frequency matches the bulk and square calculated by referencing it to the surface. And this is directly returned as part of the POC2 output. So this is not something I'm diagnosing offline. This is the plot from the new FOSSEE simulation. So the top panel is showing you the mixed layer depth from the simulation. The top right is from the climatology by Holt and others. So in this plot, I'm using a slightly different definition of mixed layer depth to enable comparison with the observations. So here, the criterion is a difference in delta rho of 0.03 from the surface. And the bottom two panels are model minus obs, and the bottom right is the fractional change, model minus obs by obs. So you still see very large biases in the Labrador Sea. It's almost nearly equal to the error is nearly equal to the actual value of the mixed layer depth itself. But if you contrast this with the next slide, which is the set of the same for plots, but for the original FOSSEE simulation, the difference is very, very slight. There's a slight reduction in the deep mixed layer bias in the Labrador Sea region. So I'll switch back and forth again. So this is with the submeso model, and this is without the submeso model. But again, it's not solving all our problems, and it's also slightly enhancing the shallow bias in some other regions further south. So this is a plot of the SST from the original FOSSEE set, just to give you a sense of what are the swings in SST as you go from cycle to cycle. So the green, the very spiky green curve is the monthly globally averaged SST, and the black is the annual. And because the nature of FOSSEE simulations, you have the non-physical jump at the end of each cycle because the forcing is going to cycle again. So there's going to be an initial adjustment period at the beginning of each cycle. So this is the change in the globally averaged SST between the new FOSSEE simulation and the old FOSSEE simulation. So the top panel is the globally average value. The middle panel is the delta SST only for the northern hemisphere, and the bottom panel is the delta SST, excuse me, for the southern hemisphere. So the values are not that big. It's barely 0.01, but you do see a very clear seasonal cycle. So at the start of each year, as you enter the winter season, you expect the submesoscale activity to become more vigorous in the northern hemisphere and in the southern hemisphere too. So which is going to warm up the upper ocean as it pumps up heat through these vertical heat fluxes. And you can see that at the beginning of each year, the simulation with the submesoscale parameterization has a higher globally average SST, and then it drops down, and then it picks up again during the next winter season. So these are some globally averaged heat budgets. So this is for a low resolution FOSSEE set. So this one we only have 4 cycles. So this is for the 4th FOSSEE cycle. So on the left, you're looking at the advection terms, the vertical diffusion terms split into the non-local and the local term. I'll just show you in a second what they are. And then the red is the solar penetration, and then the cyan curve is the horizontal diffusion, which combines radii, GM, parameterized sub-mesoscales. And I think that's it, yeah. And then the black dashed line is just the temperature tendency. So the leading order balance is obviously between the solar penetration and vertical diffusion. And the two blue curves are basically the, if you look at equation 5, the first term on the right side is the familiar down gradient diffusion term, and the second term is the non-local term. So the plot is showing you the negative divergence of both of these terms. The first term on the right side is what I'm calling the local, and the second term, the negative divergence of that I'm calling it the non-local term. So on the plot on the right, what I've done is it's basically the same heat budget, but I've added the red and the blue in the left panel. So I've combined the solar and the vertical diffusion. So it's the balance at the next order. So the leading order balance is shown in the plot on the left, and the next order balance is the plot on the right. So here the submesoscale term is the dominant source term at the next order. So this is for the lower resolution FOSSI. Then this is for the high resolution FOSSI, the one with the submesoscale model. So it's at the leading order, nothing changes. The balance is still between solar and vertical diffusion. And at the next order, once again, you see that the submesoscale tendency is the dominant source, and that is balanced by the residual bit when you combine the vertical diffusion and solar penetration. That's the purple curve. So I should point out that the residual curve in the bottom, the panel on the right is not the same as dt, and that's because of the restoring that I mentioned early on. So in the fifth cycle, there was some restoring of temperature, and that term was not really saved as part of the output. So I cannot balance the budget based on the output that I have, but I still know what the dt is because I have restart files and I can compute the actual change in dt. And this is the heat budget for the FOSSI simulation without the submesoscale models, and not all the terms that I had for the new FOSSI simulation were saved in this set. So I didn't have the vertical diffusion terms saved separately, the local and the non-local, but I have the dt based on the restart files. So what I'm calling the residual in the left plot, you can interpret that as mostly coming from the vertical diffusion. And there is no submesoscales in this set. So the next order balance, the plot on the right, it's mostly a balance between the convergence of the vertical eddy heat flux, because this is the globally averaged plot. Lateral fluxes are not going to enter the heat budget through there is no lateral convergence. So the balance, the next order, is mostly between the vertical flux convergence and the residual when you combine solar and vertical diffusion. So this is a plot. This is zooming into specific regions. This is a plot of the resolved eddy advection in two regions. The top is showing you the Kuroshio, and the bottom is showing you the North Atlantic. So the plots on the left are basically the divergence of U prime, T prime at the shallowest model level, which is 5 meters. And on the right, you're looking at the submesoscale tendency at the same depth. Again, this is part of the model output, so I don't have to diagnose this offline. So it's clear that even at 0.1 degrees, the contribution from the parameterized submesoscales to the temperature tendency is at least as strong as what you get from the resolved eddy advection. So Finally, I want to look at some vertical heat fluxes. So these curves have been obtained by averaging over these boxes that you see in this plot for the Kuroshio and the North Atlantic. So for the North Atlantic, that box basically is the Gulf Stream region. I haven't shown any SSH contours, but they pass right through that region. So if you look at the Kuroshio, you see 4 curves. They are from 3 of those are from the new FOSSI simulation. The curve with the solid circles is the resolved contribution to the vertical heat flux. And the vertical heat flux itself is computed using the equation below. So the angle brackets are monthly averages. All the terms on the right-hand side are available as pop output. So I have WT averaged over a month, and I had monthly averages of W and T. So I can get the W prime T prime averaged over a month and then across the length of the duration of the entire simulation. So the interesting thing is, as you turn on the sub-mesoscale model, the resolved flux actually goes down. And you can see that by comparing the red solid and the blue solid curves for both the Kuroshio and the Gulf Stream regions. And I suspect this might be because this is not a fully coupled simulation. They are being forced by the same atmospheric forcing. So it's possible that this is just a sign of the control exerted by the atmospheric forcing. But the resolved flux really goes down as you activate the sub-mesoscale parameterization. The sum, however, of the resolved and the sub-meso, that is more comparable to the blue solid, which is the original FOSSI set without the sub-mesoscale parameterization. And I should also point out that the way I compute the sub-mesoscale flux in panels A and C is I only have the monthly average vertical velocity and the monthly averaged temperature. And I just form the sub-mesoscale flux by multiplying the two. So that's not the full sub-mesoscale flux, because you can also have contributions that are coming from fluctuations. So the panels in B and D, when I'm showing you the flux convergence, the red solid line in panels B and D is actually not simply equal to minus d by dz of the flux in panels A and C. Instead, the pop output actually returns a field called sub-mesoscale temperature tendency. So that is the full contribution coming from sub-mesoscales to the temperature equation. And you can see that because if you look at the fluxes in panels A and C, if you look at the solid red and the solid blue line, they are very nearly equal as you go towards the surface. But clearly the corresponding flux convergence term is very different in both panels B and D, and that's because of this reason. The dashed red line in panel A is just a part of the sub-mesoscale flux. It's not the full flux. But the tendency in panel B is showing you the full contribution from the sub-mesoscales.
Can you start wrapping up, Sanjeev?
Yeah. So I think I need a couple more slides and I'm done. So the green curve here is from a fully coupled simulation of the North Pacific, which permits sub-mesoscales, using WRF and RONS at 3 km resolution. And this is giving you even larger fluxes in the Kuroshio. It's almost twice as large as what you get from both the other simulations. And this is just same thing zoomed near the surface. So this slide, the reason I'm showing you this slide is the plot on the left is from a paper by Zhao Jing and others in 2020. And this is an analysis of high resolution coupled CESM. but without any submesoscale. So it's not resolved or parameterized. And the vertical flux profile they see is very similar to what you see in typical submesoscale resolving studies, which is you have a peak that's order 100 watts per meter square, and the peak is shallow within the top 100 meters. And what my results are showing is that if you add a submesoscale parameterization, even at 0.1 degree, you can expect an additional vertical heat flux of roughly the same amount. So yeah, I think I'm over time, so I'll just leave this as my final slide. Thank you.
Okay, thanks, Sanjeev. Questions for a quick question for Sanjeev. We're running a little behind. Bill, I see you unmuted. Yeah, go ahead.
Yeah, I have a model development question. You showed the submesoscale effects, but those are in models that have been tuned to simulations without any submesoscale. So if we put in a submesoscale, what should we do with the parameters that have already been set without the submesoscale? Should they be altered, or should we retune everything? What do you, just on a general development issue, how do we proceed when you put in a new term that seems to be quite, it's certainly not negligible, let's put it that way. What do we do?
Yeah, it's a great question, and I don't have a clear answer at this point. I guess part of the reason for doing this exercise was just to get a sense of how things change if you add this model at high resolution POP data sets. So yeah, I don't have a good answer.
Maybe we should discuss this in the discussion, because
Sure.
I think it's an important one.
Okay, I think there are more questions come up on this topic. We can address them at the break. But let's move on to Annalena, the last talk of this morning. So, Sanjeev, you could stop sharing.
Stop sharing.
Okay, I'm assuming everyone sees
Yep.
my screen. Thanks.
Good.
Hi, everyone. My name is Annalena Deppenmeier, and I'm a project scientist in the ocean section at NCAR. I would like to show you our recent work on diabetic upwelling in the tropical Pacific. I've already talked a bit about this last year, focusing on the longer timescales of interannual variability. This time is going to be seasonal and subseasonal variability. This work's done with Frank Bryan, also at NCAR, Billy Kessler at NOAA PMEL, and Luann Thompson at the University of Washington. I have two little sort of icons here, which is one of the takeaway messages from my talk, which is that diabetic upwelling is mostly driven by vertical mixing and solar penetration. And in some instances, we have a secret sauce ingredient that we'll encounter at the very end of this talk. Okay, but before we diagnose diabetic upwelling, let's make sure that we all are on the same page in understanding what it is. So if we look at the tropical Pacific along the equator and a cross section from west to east here, we can identify the thermocline, which is shallower in the east and deeper in the west. And we know that there's the equatorial undercurrent, very strong current flowing eastward along the thermocline roughly, and then there's a surface current that's flowing westward, leading to a very large current shear between the two. And then in the east, where we have these the shallow thermocline and colder sea surface temperatures, we have upwelling W, which we usually depict with this arrow sort of pointing upwards across the thermocline. But we can really think about this upwelling a little more, and it consists of two different components. So one of them is, we've seen that the equatorial undercurrent flows along the isotherms, along sloping isotherms. So this vector has a vertical component, which is part of the upwelling, which would not be altering any water parcels or taking up any heat. And then we have another part of the upwelling that's the diabetic upwelling that I'm talking about mostly, is one where we have a water parcel sitting here underneath the thermocline or underneath an isotherm in the thermocline. And through some process, it crosses the thermocline, so it takes up heat and has now a different temperature than it had before. And this is a water mass transformation process. So the parcel has changed its properties in the temperature class from colder to warmer. Therefore, it has taken up heat, and we can describe the rate with which this happens by this cross isothermal velocity that I denote WCI. So when I talk about water mass transformation or cross isothermal velocity, this is the process that I'm talking about. Okay, so that's the idea behind diabatic upwelling. And now we need a framework to analyze it. And so I'm just going to walk through this equation. We diagnose the cross isothermal velocity from two different ways of calculating it. So one way is projecting the temperature direction into the cross isothermal direction. And then we need to account for the movement of the isotherms, because if the parcel moves in the cross isothermal direction, but the isotherms sort of moving away from it, then the parcel is just chasing the isotherms and we're not having any cross isothermal velocity. So this is one way that we can calculate the cross isothermal velocity. And then we can show that we can connect this to the heat budget equation, which allows us to diagnose the specific physical processes that are behind this cross isothermal velocity of this water mass transformation. So one of them, one of those processes that contribute is solar penetration, and then we have vertical mixing. Because it's a model, we have horizontal mixing, so the two are split. And then we have a covariance term that arises from our averaging operator, because we're not calculating everything instantaneously. So I just want to stress two things. One is that these calculations are two different calculations. So I arrive at WCI from this equation, and then I attribute WCI to the physical processes via this equation. And another thing that I want to point out is that the solar penetration and the vertical mixing contribute not in the absolute magnitude of their heat fluxes they induce, but the vertical divergence of the heat flux, dIdZ and dJdZ here. We'll come back to that later. Okay, so now we know how to calculate WCI. Which data set am I using? I'm using a 1/10 of a degree pop run forced with 3-hourly interannual JRA, realistic surface forcing. And for 36 years of this run, we have a full heat budget output, which allows us to calculate these different contributions to WCI that I've just introduced. And here I'm just showing you a snapshot of SST, 1 5-daily average of SST from this simulation, and where you can see or can get an idea for the spatial scales that we can resolve with this simulation. Okay, so moving on to diabatic upwelling. I know I'm going to be talking about variability mostly, but I just wanted to start us off by having a look at the mean. And so this is the 36-year mean of diabatic upwelling in the tropical Pacific. So a couple of things to note. It's a very thin signal, really closely located on the equator, not stretching out very much at all. And it's sort of active, let's say, east of 150 west, and it's getting stronger as we go further to the east and weaker if we go to the west. And so to maybe get a feeling of what these values mean, so this is 0.5 meters a day and the maximum in diabatic upwelling of parcels that move across isotherms. And in this case, I don't know if I said it already, it's across the 20-degree isotherm. So if we want to look at this water mass transformation, it's useful to look at isotherm or temperature space rather than Z space, because the isotherms move in Z space with time, and we would get a sort of smeared out signal. So we always want to be looking at temperature space. So this is the diabatic part of the upwelling. And I've mentioned earlier that there's two components of upwelling. We have an adiabatic and a diabatic part. And so here I'm just plotting the total vertical velocity, of which the diabatic is one part. Note that the color bar here has changed, the scale has changed. We're now allowing for 1.5 meters a day of upwelling. And you can see that they are clearly related, the diabatic and the total upwelling, but you can see that maybe the ratio with which the diabatic upwelling contributes to the total upwelling changes, depending on longitude. So here we have the strongest signal of total upwelling sort of between 140 and 120 west, and we have the strongest signal of diabatic upwelling further the east than 120. So maybe in the east, the diabatic component would be more important relative to the adiabetic component. Okay, that's just sort of an overview of the mean situation. Now let's start talking about variability. And so I'm showing you this video of water mass transformation across 20 degrees for the mean seasonal cycle. And you don't need to be recognizing which month shows you which signal. This is just to give you an indication of the variability, which is rather large. So we do see large variability with the seasonal cycle of this diabetic component of the upwelling. And I will just say one more thing about this diabetic upwelling in general. We're interested in it because this is the part of the circulation that's A, poorly constrained, and B, really matters for heat uptake into the ocean, because we're taking heat up into the parcels that cross these isotherms. Okay, so let's look at the seasonal cycle and diabetic upwelling in a little more detail. And I'm choosing this location here where you can see that there's a lot of variability. So again, we are looking in temperature space here. And then on the x-axis, there's time of the mean seasonal cycle. And I've denoted the 20-degree isotherm here because that's where we were just looking at in this video. And so we can note one thing. From this video, we kind of might have gotten the impression that the diabetic upwelling really dies down at certain times of the seasonal cycle and really doesn't exist anymore. It's very small. And if we now look at the whole water column, we can see that diabetic upwelling is in fact occurring throughout the seasonal cycle, but it moves with the water column. So the reason that 20 degrees Celsius is relevant to us is because that's how we usually define our warm water volume, above the 20 degrees Celsius isotherm. So we might be interested in how much this diabetic process contributes to that. But it's a somewhat arbitrary decision that we made connected to this warm water volume. And if we're interested in the process, we might be looking at the entire column, which is what we're doing here. So we can note two things, that there's, well, several things. So there's diabetic upwelling happening throughout the seasonal cycle in the water column. And there's two maxima. One is in boreal spring and one is in boreal summer. And it sort of stretches out a little bit. And these maxima are in very different parts of the water column. The hatching here denotes when isotherms are present less than 50% of the time. Why did I do that? I show this here in order to indicate if we're close to this hatching in the water column, it means we're really close to the surface. So here we have this really close to the surface sort of shallow maximum of diabetic upwelling in boreal spring, and a deeper one that's more close to the thermocline or in the thermocline in boreal summer. So now we can go ahead and attribute the diabetic upwelling to the different physical processes via this heat budget calculation that I mentioned earlier. And so what I'm showing here is not, it's the contour where vertical mixing contributes to the diabetic upwelling with 0.3 meters a day. So let me say that again. These lines indicate the regions or the regions in the water column where vertical mixing induces more than or equal to 0.3 meters a day. I chose this because if we look at the scale here, 0.3 is a significant contribution to the total signal. And I'm not overlaying entire contours because then my plot's getting really confusing. So we can, with just this knowledge, we can draw a major conclusion, which is look at this maximum here. And if you just imagine this, the outline of these dashed lines to be the contour of 0.3, they do increase sort of in the middle of this signal. And we can see that here, the diabetic upwelling maximum is really located right in the middle of this vertical mixing driven diabetic upwelling. So this peak here is driven by vertical mixing. And then we have this earlier maximum that's sort of sitting like on the edge of this 0.3 meter per day contour. And the signal itself is clearly larger than 0.3. So there needs to be another contributor here that induces this diabetic motion. Oops, sorry, wrong way. And that is solar penetration. So now I'm just choosing a different way of showing you the contour of 0.3 meters a day for solar penetration. And you can see that while sort of in end of boreal spring, throughout summer and fall, we can see that solar penetration really only reaches the very shallow surface layer and doesn't really coincide with this maximum in WCI, which is solely driven by vertical mixing. But here, where we have this shallow maximum, we have a large contribution of solar penetration to the signal. So this means that we have two regimes of diabatic motion in the tropical Pacific. One is in the thermocline that's driven by vertical mixing, and one that's closer to the surface in the shallower waters, which is due to solar penetration. And this was just one location. We can look at this throughout the cold tongue, further to the east or further to the west. And the picture is pretty much the same, just that the magnitude is a little stronger here of WCI, which we've already seen from the map before. And then we can go one step further and look at what drives this vertical mixing induced diabatic upwelling. And so we already know that in our model, the vertical mixing scheme is dependent on the shear. So if we plot the mean vertical shear in the same temperature coordinates as we plotted the diabatic upwelling, we can sort of see that the maximum in vertical shear temporarily coincides with these maxima in diabatic upwelling. They're not entirely co-located in the vertical, because the higher vertical shear induces a higher turbulent heat flux induced by vertical mixing, but we need to be looking at the vertical heat flux divergence, and I'm going to summarize that in the next slide. So as a recap for the mechanism that's driving variability on the seasonal scale and diabatic upwelling, we're looking at a cross-section across the equator, where we see that we have this strong eastward flowing equatorial undercurrent that induces vertical mixing in this part of the column, and then we have solar penetration reaching here. So those two contribute to the turbulent heat fluxes going into the ocean, which have this shape. But we need to remember again that it's not the absolute turbulent heat flux that induces our diabatic motion, it's the divergence of this heat flux. And so the heat flux divergence basically says that if it's negative, we take heat out of this area of the ocean and put it into this area of the ocean. And so those two together, then the two divergences of these heat fluxes make this WCI signal, this cross isothermal velocity signal. And there's one detail here on this slide that I wanted to point out, and that's, remember that we project our motion into the direction of the temperature gradient, so perpendicular to the isotherms. And in the region, for example, in the thermocline, where the isotherms are roughly horizontal, we will have a diabatic motion that's actually vertical, so corresponding to the upwelling as we usually think of it. But if we're going higher up in the column, closer to the mixed layer, where the isotherms are rather vertical than horizontal, we get motion that's more horizontal rather than vertical. So this is usually coincides with solar penetration. And so this solar penetration driven diabatic regime that we've seen in boreal spring is likely actually off equatorial motion rather than vertical motion. Okay, so this was the seasonal variability. I promised to talk about sub-seasonal variability too. And so let's have another look at a video where we can get a little bit of an impression of this variability. So these are 5 daily averaged fields, and I'm just showing you a short period. There's a lot going on. You don't need to get every detail, but there's one thing that you might notice, and it was just happening right here. So let's wait for it to happen again. Here, so there's these north filaments that extend north and move westward. You might recognize them as looking like tropical instability waves. I did not overlay sea surface temperature because this plot is already messy enough, but they do in fact coincide with the passage of tropical instability waves. So let's look at that in a little more detail and without so much movement so that we can focus on it a little more. And I'm choosing to look at this along to north because, as you can see, this is kind of nicely sitting in the middle of these tropical instability wave fronts. Okay, so if we look at a Hoffmiller That's times increasing here on the positive x-axis, and we have longitude here of sea surface temperature. And then here in black, I've indicated tropical instability wave kinetic energy. So this is to say, if this black arrows or black values are large, we have a tropical instability wave passing. And you can kind of see this here also by this westward propagation of cold temperatures in these streaks that coincide with the high tropical instability wave kinetic energy. So this is just one example here that I've chosen. And this, again, we can see these tropical instability waves passing in the SST field. And so what does this do to our diabatic upwelling? And if we look at diabatic upwelling in the thermocline, we can sort of see, see these streaks that coincide. If I overlaid the sea surface temperature, you would see that it actually really does coincide with the passage of this tropical instability waves. So there seems to be a modulation of tropical instability waves that change or enhance the diabatic upwelling in the tropical Pacific. And now we can go in again and look at why or which physical processes are driving this. And from the intuition that we've gained from the seasonal cycle, we might be thinking that it's enhanced vertical mixing that's driving this, because that's usually what's driving diabatic upwelling in the thermocline. And we can see here that we do see these streaks, but their magnitude is much too small to explain the entire signal of WCI during the passage of the tropical instability wave. So now we can, solar penetration is not going to do much because we're sitting in the thermocline below the reach of solar penetration. And we can look at this covariance term, which, if you compare these two panels, you can see that this explains much more of the signal in diabetic upwelling. And so this covariance term is a little bit tricky because it doesn't just describe the eddy on the time scale of the tropical instability wave, because this is a covariance on sub-5 daily timescales. So this could be induced by the covariance of the front passing, the change in the isotherm depth. And so these are the sub-daily unresolved scales that we can find back in our WCI signal. That's the secret sauce ingredient. Okay, I also looked at this on the equator. I don't really have time to go through this. Let it suffice to say that there's a different mechanism happening on the equator, which is much more related to the vertical mixing as we might have estimated. And I'm happy to talk about that more later on. Thanks.
Okay, great. Thanks,
Stop
Anna.
here.
Okay, questions for Annalena? Marcus.
Yeah, this was a beautiful set of diagnostics. Thank you. Can you say more about the covariance term? That looks rather interesting, but
Yeah.
is there some physical meaning behind that?
Yeah, so the way that this covariance, so we used to say that this covariance term is the eddy term, right? It's the covariance of perturbations on the timescales lower than 5 days, because we diagnose it on sub-5 daily timescales. The problem with calling it the eddy term is that when I say eddy, everyone thinks of tropical instability waves, and it's not capturing the entire tropical instability wave because the timescale is too short. So the way that I'm interpreting it now is that while the tropical instability wave has a longer timescale, if you look at one location, the passage of the front that might move even on those shorter timescales induces a covariance of the temperature gradient and the flow that we can find back in this inducing this WCI. But
is this a horizontal eddy term or a vertical one?
So it's not the horizontal mixing, it's not the parameterized term. I can't say if it's, I don't think we can say at this point whether it's a horizontal or vertical term. Okay. So it's not the horizontal parameterized mixing. That's basically very low. We kind of expected this to maybe take over during the passage of the tropical instability waves, but that's not what this term is. It's really the covariance of the passage of the front with the meridional velocity, for example, inducing this WCI. Mm-hmm. Yep. But I'm looking into this more. So, thanks.
Okay. Any other questions for Annalena? Bill, did you have another question?
Yeah, it was related to what Marcus asked, but basically, this covariance term would go to zero as your analysis time step went down to the time step of the model, correct?
Yep, that's correct. Yeah.
So it's just because you're doing 5 days versus every time step. And you calculate it, I think, as a residual. You've got two ways of calculating this. One is you had two equations for it. And then one had the covariance, and you just do that as a residual. Is that how you do it?
No, it's not a residual between the two. You mean these two parts of the equation?
You actually do the time step by time step and then do the correlation that way.
So on the 5 daily, we take the mean temperature advection versus the.
Anna, why don't you show the equation?
Yeah.
On that slide.
Okay.
So that equation on that slide is the evolution of the 5-day mean temperature.
Right.
And we can compute the mean, the advection from the 5-day mean velocities available, and we can compute the total advection, which is accumulated online, and we can compute the covariance as the difference between those.
Yeah.
Right, exactly. So it's because you do the actual calculation online and do the proper averaging, at least in one, and then, okay, that's what I thought.
Yeah, so, right, so it's not the difference between these two terms, but it's a explicit calculation that we take a difference, yeah.
I mean, a subtle point here is this is the 5-day mean diabatic upwelling across the 5-day mean isotherm.
Yep.
So,
Correct.
so there is actually some additional covariances which we aren't able to capture, which are like the covariance between 1 over grad theta and all of those other terms.
Right.
So, anyway, Marcus, you had a follow-up?
Yeah, I have one more. Where would the diurnal cycle be in there? I mean, I think Jim Moon seems to think a lot of the mixing has to do with the diurnal cycle or nighttime convection. And would that be part of your covariance terms, or where would you see that?
Well, I think so, because we accumulate the accumulated heat flux, for example, due to vertical mixing over the 5 days. I can't really say it's coming from, so this is it's in the vertical mixing term. It doesn't show up as a separate term. So in order to look at this, that I would have to do this calculation on very short timescales to say, well, this is happening during the night and this is happening during the day.
Okay, thanks.
Thanks. And there's we do have a higher resolution product that we're going to look at this with. So hopefully we can maybe get to some of those questions.
Thanks.
Thanks.
Okay, that wraps up the morning session. There were a few leftover questions for Steve Yeager. I don't know if anyone has lingering questions, if Steve is still around. I think it was Peter. Anyway. Okay, well.
Well, my question to Steve was pretty much the same as Steve Griffiths.
Okay.
I wondered whether the improvements in atmospheric variables such as precipitation were mostly due to the better atmospheric resolution rather than the ocean resolution.
Yeah. We don't know.
Yeah. Because, you know, precipitation definitely improves as the atmospheric resolution gets finer. So.
Okay, Steve, any comment?
No.
Did you want to respond in any way, Steve?
I said no, I have no comment. We don't
Okay.
answer Peter's question.
Yeah. Okay, Bill, your hand's still up. Did you have another question? Nope. Okay. All right. Well, we'll adjourn then till 1300 Mountain Time, about an hour and a half from now. We'll resume with Ali Mashak. I think the Zoom just stays open this whole time. So if people want to socialize during your lunch break or dinner break, whatever time zone you're in, you're welcome to hang out on the Zoom or come back at 1 o'clock. So I will see you back at that time. Ian,
Hey, Frank.
not seeing our first speaker yet. He was on this morning, so.
Yeah, the numbers are just slowly starting to come up.
Yeah. I have this problem with, I plug in my laptop to my monitor and that provides power. And like 1 out of 10 times, the monitor's working, but it's not supplying power to my laptop. And this morning I didn't notice that was the case, and it basically started shutting down because I had no power. So anyway. Good, there's Ollie.
Hi, everyone.
Ollie, good to see you.
The same. How are you?
Nice. This hour?
Yeah, it's not that late. Okay, so should I share my screen?
We can try it if you like. Yeah, Elizabeth, could you take down that?
Sorry, I asked her to put that up.
Am I going first, or is
Yeah,
someone?
yeah. We'll probably wait a minute or two. People are still
Okay.
rolling in.
Okay, so
See if it comes up.
Yeah, numbers are still coming up.
Yeah.
can you see?
Yep. Yeah. We'll wait a minute to get going.
I'm trying to cover a very broad audience.
Good.
So I can also show this to kindergartens.
I don't remember how many people were here at the beginning. We won't wait too long before we start.
Yeah, I think we had about 50 this morning.
Frank, should I start with
Yeah,
you?
whenever you're ready, Ian. Go
Yeah.
ahead.
Okay. Welcome back. Thanks everyone for being here. Frank has moderated the first 3 sessions. Great job, as I've been in and out with teaching and committee. I'm going to give him a break this afternoon and moderate this session. So remember, share the air. We had that slide up earlier in the discussions and questions. If you do want to ask a question, please use the raise hand function in Zoom. If you want to put a written message in the chat, I'll monitor that too and read it out if you have a question for the speaker. We have a medley of talks this afternoon, and then there is going to be time at the end for follow-up questions and discussions. I'll try to keep us close to on time here. Our first talk is from Ali Mashayek, Imperial College, and you can read his title there. So Ali, thank you. Take it away.
Yeah, thanks, Ian. And thanks everyone for fitting me in the schedule last minute. And nice meeting many of you virtually. So I have a very bad cold, and so I apologize for my face and for my voice. And I'm in London, so I won't be. I can't stick around until the very end when you have the discussion. But I hope to have conversations with some of you, in the coming days about this. So this talk is motivated by a question that I was asked when I was talking about my work, which was like, does small scale mixing actually really matter for the climate scale, for the climate system? And the question was like, does it really matter? And I didn't know the answer to that. So this is sort of our collective effort to see if it really matters and on what time scales. And I'm very selective if you look at, if you think about the sort of zoo of instabilities and processes in the ocean that can create dipycnal mixing. I'm just focused on shear induced turbulent mixing. So you can think of tidal mixing, lee waves, wave breaking in the interior, near initial shear sort of at the surface propagating downward. You can think of overflows, boundary turbulence, but like I'm not talking about dipycnal mixing because of convection or double diffusion. And the main point that I'll try to make is that there seems to be an optimal state in ocean mixing in which mixing is really efficient where it really matters. And I'll explain what I mean by that. And that's why I use the word Goldilocks mixing. But to get there, I need the system, either conceptual or in a model, to have 2 degrees of freedom. One is that I need a system in which, as the ocean changes and the stratification changes and the forcings like tides and winds change, these processes can adapt to that. So the distribution of energy in the system should change as the climate changes. And then the stratified turbulence should also adapt to it, meaning that when these waves break and actually create dipycnal mixing, the partitioning of that energy into mixing versus dissipation, the so-called efficiency, that should also adapt to this. And the point that I'll try to make by the end of the talk is that these two go hand in hand. And if you just give the system 1 degree of freedom, it can overshoot or underpredict. But if you let them work together in terms of the distribution of energy and then partitioning of that into mixing and dissipation, together they can create sort of an optimal state. And so I'll briefly talk about the physics of small scale turbulent mixing and what I mean by Goldilocks. And then that would be related to individual turbulent patches and when they break. And then I'll try to talk about how we go from that to sort of a regional bulk measure of mixing that inevitably involves statistics. And then I'll start talking about what that actually means for the larger scale circulation in terms of deep upwelling and downwelling. And I'll go through 2 case studies in the end. One is the impact of this story for AMOC and its internal variability, and the other one on Southern Ocean air sea carbon fluxes. I hope to be able to make it all the way to the last one. So I imagine most of you know, or all of you, the Goldilocks story, but if you don't, just a brief sort of refresher. The story goes as just, Goldilocks is walking in the forest, sees a house. She just walks in like any sort of reasonable small girl would do in the middle of the day in a jungle. But here's the key. She comes across 3 bowls of porridge. One is hot, one is cold, and the other one is sort of the right temperature. And then she wants to sit. One chair is tall, one is short, the other one is the right height. And then she gets sleepy, she goes take a nap, and one bed is too hard, one is too soft, and the other is one that's optimal. And that's what I mean by Goldilocks. Not too hard, not too soft, not too hot, not too cold. And I'll argue that ocean, when I refer to optimal mixing, is when you have the right balance of stratification and energy available to turbulence to give you optimal mixing. Because stratification and turbulence have sort of this love and hate relationship in the sense that stratification suppresses vertical motion, but at the same time, it gives rise to all these instabilities and density stratified turbulence. So the right balance between them gives you Goldilocks mixing. So this story in this version has a very strange ending in that the 3 bears arrive and they're surprised and Goldilocks wakes up and leaves. So that's a separate talk. So I'm going to skip that. The very quick sort of 1 slide update on the sort of parameterizations of efficiency of mixing, which is one of the components of the recipe that I'm moving towards. So if you just look at one wave breaking, if you just look at the top row of this life cycle, and the colors, you can think of them as density. So this is lighter than blue is lighter than red, and as they mix, they sort of form this mixed water. There are 3 scales that we care about. I mean, in the simplest representation. One you can think of as LT, or the Thorpe scale. That would be sort of the representative size of this overturn. And that's a measure of the APE, how much available potential energy you're storing in a wave as it rolls up. And then on that APE, little eddies that you can represent them with LO feed and they grow. And there is a phase where these eddies get large enough that they're almost the same size as the original overturn. And that's the most efficient way of extracting energy from the background shear and mixing. And so that would be basically here. And I will show you statistics that most turbulent patches in the ocean that we see are actually near here. So in a sense, the turbulence in the ocean, when it's really energetic, it really grows into a turbulent mode, and it's energetic, it's very efficiently mixing there, and then it decays sort of rather quickly. Now, the key points to take away from here, one is that LO depends on epsilon rate of dissipation of kinetic energy and stratification, the buoyancy frequency. Now, just in terms of progress of our ability to parameterize this, the efficiency of mixing, which is what we need from a modeling perspective. And let me actually define efficiency. So this is the flux coefficient. This is not actually efficiency. Efficiency would be mixing divided by mixing plus dissipation. But this is practically what we use. And traditionally, we parameterize this as in terms of a buoyancy Reynolds number, which is the ratio of Osmedov to Kolmogorov scale. And this is just data from 50,000 turbulent patches, 6 different experiments. The point of this plot is to show that parameterization was hopeless. But we can parameterize it in terms of the Osmedov to Thorpe scale ratio, and it actually really collapses. So we have this analytic parameterization that is entirely based on physical grounds, Kolmogorov theory, mixing length theory, criteria for shear instability, and one more component. And you can actually derive it up to even its only coefficient, and it actually works pretty well. And so there has been significant progress in our ability to represent the mixing properties of individual patches. And I'm going to use this, and I refer to this as Goldilocks mixing. And the Goldilocks comes from the fact that when LO and LT are close, which would be sort of the center of this, you get really optimal mixing. Now, that's physics of individual patches. And the way we actually get data points that I showed you on the previous slide is, this is a transect from the Brazil Basin tracer release experiment, and where they did macrostructure profiling. And for each of these profiles, these are patches that have been identified, and red and blue for each patch is the measure of LT and LO, just to show you operationally how we get them. And if you ask the question for one wave, like from a simulation that I showed in the previous slide, how many times should you sample one wave so you can get its net mixing correctly? You find that you need about 20, 30 samples. So this is sort of normalized flux, net flux, and that this is the standard deviation, and that's basically sample size. So you need to sample one wave 20, 30 times to be able to get the right result. And that's hopeless. We never have that. If you're lucky, you can go through a wave sort of once. But there is hope in that when you look at the statistics of these and the ratio of ROT, you see that it has a sort of log normal looking distribution. And this is from the same 6 data sets, but there's a literature on this, and this seems to be universal. It's not exactly log normal, but it is centered around ROT being 1. And that's the key, centered around the Goldilocks limit. And if you divide the data into quartiles of epsilon, so from black to blue, you go towards stronger turbulence. For strongest turbulence, the peak actually moves even closer to 0, which is the Goldilocks limit. So there's promising statistics of ROT. That would be another component of the soup that I'm making. The first one was this parameterization. The second one is the statistics of ROT. And then we can look at the statistics of turbulence, because everything I showed so far is about patches. So we get full profiles of data and we identify patches. But if you look at the entire profile, and now I'm looking at the collection of data that was that is available through the scripts as a part of the CPT on ocean mixing. So these are like 850 full depth macrostructure profiles. If you look at epsilon, rate of dissipation of kinetic energy from them, you see that it has a sort of perfect log skew normal distribution. I mean, traditionally we represent distributions of epsilon as log normal, but the key is that that's not correct, and is quite skewed. And the skewness is really important because this is epsilon and it varies over 6 orders of magnitude. And it's the tail that really matters because those are really strong turbulent patches. So there is a log skew normal distribution that can be fit to data that sort of really accurately represents the tail and also does pretty well for the whole distribution. And that seems to also be universal. And that universality of the distribution of turbulent kinetic energy dissipation is sort of a third component in the recipe that I'm making. And we can actually think about why it should be log skewed. If you were to sample one process over and over, it would tend to get a log normal distribution. But if you have many log normal distributions that non-linearly interact, which is the case in the real ocean, then you can show that statistically you start skewing the tail of that. So we sort of do understand how we get that. So far I give you 3 components, right? A parameterization for individual patches in terms of physics of mixing, the distribution of their sort of RO to RT ratio, which is key for the parameterization. And we have also a sort of universal distribution of epsilon. And that's really key because if you remember, LO, which was the Azimuth scale, was epsilon divided by N. So this we can, if we assume this universality for dissipation of kinetic energy, from that we can work out LO. From the universality of LO over LT, we can work out the distribution and so forth. That's the recipe. Now, if I were to implement this in a model, the model would require some information about the energy that's available to turbulence. So the energy that's available that would either go to mixing or dissipation. Now, where does that come from? That can come from different sources. And there's been sort of recent interesting progress in how we can represent them. I mean, in particular works of Casimir de Laverne and others that have sort of used ray tracing and sort of split the tidal mixing components into different sort of contributions from wave-wave interactions, scattering, critical slopes, shoaling, etc. And if they have these 2D maps that you can map into the interior based on the stratification, that's the left one and left panel. And the right panel is sort of the Q, which is from Matthew Alford's work, which is basically the energy input from winds into near inertial waves. And it's the Q, meaning that it's a ratio of the energy that sort of dissipates locally versus what goes to the far field, and we don't account for. So these can be used for a given stratification as a model is running forward to update the energy distribution coming from the top and bottom. And so that gives me 1 degree of freedom. And then on top of that, I can basically assemble a recipe for the stratified turbulence and then let it do sort of interact in an adaptive fashion. So the soup that I'm making to come up with this bulk gamma goes as this. Imagine if this is a coarse grid of a climate model, which we don't resolve what's happening inside, but there's so many sort of turbulent patches within that can contribute to mixing. So I can imagine that from maps like this, I can construct a power that's available for that grid cell. And then I can get that power and translate it into a distribution of patches that has this universal form of sort of log skew normal form in terms of the total epsilon from that and this bulk stratification in that cell. I can construct an LO over LT distribution. And from that, then I can apply the parameterizations of efficiency of mixing to individual patches. And by the end of this, I can basically add up the mixing of all of these patches that are statistically represented to get the total mixing in that domain. And the total mixing in that domain divided by the total epsilon of that domain, the total power, which I started from, would be a bulk measure of gamma. So it's the same concept, but now it's bulk in that this is a total power in this cell, how much goes to mixing, how much goes to dissipation. So far, we've used it, we've taken it to be 0.2 based on, individual wave breaking. So it's just, it's unjustifiable on many different levels. So we can put this recipe together and get it to work. And because it's the statistical sort of, we generate statistical distributions of patches, we do it a number of times and then we get the average. Now, doing that for every grid cell, for every time step would be really costly, but one could do that for a parameter space that covers the power and stratification that's relevant to the ocean. And then you can actually fit a very smooth surface to it that's analytically reasonable. And so so then it makes it really straightforward and very cost effective to implement in a forward running model. Now, does this actually really matter? A few diagnostics. One, this is diagnostics. This is the whole recipe applied to the global ocean, to climatology, to WOS climatology, and the energy comes from winds and bottom generated mixing. And the ratio of the bulk gamma to 0.2 is the same as the ratio of diffusivity if you take all of this into account or not, or the flux, the turbulent flux. They're exactly the same. If you look at it at the shallower depth, like 500 meters, you see that there is a factor of 5 between the highest and lowest. So this has an important impact. So like the last talk that we heard before the break, that Annalena was talking about the water mass transformation rate. So this is going to have a direct impact on that. And if you look at the upwelling downwelling patterns in the deep ocean, red and blue are upwelling downwelling. The patterns aside, this is the anomaly. If you have this machinery of mixing implemented versus not, and the difference that it makes is leading order in terms of the signal. It changes the upwelling downwelling patterns to leading order. And if you integrate these over different density levels and look at the net transformation rate, you can see that it has a significant impact. And one important outcome of this is that if you look at statistics of these over different density levels, you find that mixing is really optimal in this Goldilocks state in the deep density levels most of the time. So that implies that the circulation is diagnostically, it is re-stratifying really strongly turbulent regions at the rate that keeps mixing optimal. And I think that's pretty cool. So now two case studies. So we did implement this in a forward running model. It's a low complexity model of AMOC just for the Atlantic Ocean. And the model produces reasonable stratification and we are forcing and also circulation. And we force it with the same based on CMIP6 data in terms of surface buoyancy and wind. And we basically do these runs from 1850 to 2100 for different SPs. And there are three cases that we consider. One is the ones represented with the dashed lines. And that is when we have a spatially variable but temporally constant map of mixing. So nothing is changing. And then in the second case, we let the tidal and wind energy sort of available to turbulence adapt as the stratification changes. And that would be the dashed dotted. And then we let that and efficiency, the bulk gamma, change. And a few important things happen. If you look at the lower branch of circulation, panel C, if you have a constant mixing map, which isn't changing with time, you can predict that, for example, the Antarctic bottom water formation is going to increase for different SSPs. But when you let the tides and the wind induced internal wave field adapt, that's going to dramatically change and the circulation is going to go weaker. But then when you let the efficiency be variable, it can compensate for that quite a lot. And you see it also for AMOC for the upper branch. But the point is that there is a compensation between the two factors that are codependent. And the secondly is that when you give the system these 2 degrees of freedom, you get internal variability, because then the system can, if it mixes too much, there's not much to mix, and it can tell that. And so it can wait for it to get re-stratified and then mix optimally again. And if it's not mixing much, stratification is going to build up, and then you're actually going to generate more turbulence. So if you give that restoring sort of force to the system, you can get internal variability. And that is on decadal timescale in this. Again, none of this is meant to be predictive, but the point is that there is an internal variability coming from this that we have so far ignored. And it'd be interesting to see how much of the real signals from, rapid OSNAP or the proxy records, actually, how much of that comes from this. also have important implications, like people that look at the decadal, like the past couple of decades of Antarctic bottom water formation, interpretation of those signals. I mean, if you look at this, one would be more cautious about that. And finally, this model has a simple carbon cycle. I'm not going to go into details, but the amount of difference that these make for atmospheric PCO2 or the meridional heat transport in the Atlantic are significant, just in terms of order of magnitudes. Point being that all of these machinery that I talked about can make a significant difference. So it's worth paying attention to. And one last case study before I wrap up. We did put this in SOSI, the Southern Ocean State Estimate, the BSOSI, which also has the biochemistry. And if you look at the second row, I mean, this basically shows the variations to the bulk, gamma, and diffusivity. It's constant in time, which obviously is not right, but it's better than the 10⁻⁴ that's everywhere in the standard SOSI solution. And if you look at this is the standard CO2 surface fluxes in VSOSI. If you do a run with this mixing machinery in and subtract the two, you get the difference, and the difference is significant. And if you integrate this northward from Antarctica and look at the cumulative flux at 30 south, if you first look at the first year of the perturbation, the dashed line goes from this value from red to blue. It's over 60% difference. And if you look at the 6-year mean from solid red to solid blue, it's again 40%. So it does make a significant difference. We broke it into summer, winter, 1 year, 6 years, try to see what makes it better. It can't be done because we don't have enough data to it's not constrained. Plus, it's foolish to expect us to make it better because this should vary in time, and there's so many assumptions in the recipe. But the point is that what I'm talking about can make a significant difference even on annual timescales. So, in summary, I think I've at least convinced myself that things that we've worked on over the past years can actually matter for the MOC. They can definitely matter on millennial, centennial timescales for the deep branch of circulation. They do create and allow for internal variability in the MOC that can be on shorter timescales. And then, when you start thinking about tracers, nutrients, and biology, they can actually be important on much shorter timescales. And what I find very interesting is this idea that individual waves, when they break, they're in this optimal Goldilocks state, but that seems to transcend to larger scales in that really energetic turbulence zones, especially when turbulence is a driver of the circulation, like in the deep ocean. It seems that the circulation is re-stratifying turbulent regions at the rate that keeps mixing really optimal. So that's still diagnostic, and from a buoyancy budget perspective, it would be really cool to connect it to vorticity budget and momentum budget to actually be able to show how that mechanistically works. So many people involved with this, I've listed them there, and there are a number of different publications. I'd be keen to get people they're interested in implementing some of these in the model. So happy to work with you if you're happy to do that. And we have scripts we have done some implementation, so we can actually provide scripts that can facilitate that. So I'm going to pause here. Hopefully I left time for questions. If not, feel free to reach out.
Thank you, Ali, for a nice talk. We don't have much time, but given that you're not going to be able to stick around after this, I am going to just read the one from Mehmet in the chat, and then after that, I think we'll move to the next speaker. So Mehmet asks, could you comment on what would happen to AMOC in different climate conditions? For instance, in the LGM, MOC should be weaker. Will the mixing efficiency compensate the energy to mix more and bring the AMOC back to high values? It's in the chat too, if I didn't.
Yeah, I mean, I have thought about that. I have thought about LGM specifically, and what I can say at this point is that it does make a significant difference. But I'm not confident to comment on in which direction.
Okay.
But I'd be happy to talk about it further.
That was pretty quick, and I see Frank's got his hand up, so I'm going to go for one more here.
Hi, Ollie. As far as I could see, the resolve scale shear doesn't enter your recipe. But we sort of expect that, at least in places like the undercurrent, like we heard from Annalena, the resolve scale shears are helping determine the turbulence level. How is this something that would be additive on top of a parameterization capturing those processes, or would this encompass those, or how should we think about that?
Well, that's a very good question. I mean, I didn't go into the details of the fluid mechanics of the parameterization. What I showed you can be also translated into two other parameters that actually one is Richardson number, so you can bring in the shear. So there is a version that when you actually resolve the shear that goes in directly, and when you don't, then it doesn't. So we have thought about that, but that's a very good point.
Okay, thanks.
All right, thanks again, Ali. If you could stop sharing, so then
yes,
Paul can share his.
Pause share. Did it stop or no?
It's down now. I see Paul looks like he's getting his going. All right. So, you ready, Paul?
All set. Hopefully I can make up a little time for you. Thank you for having me here today. My name is Paul Hall. I'm a software engineer at Brown University, where for the last several months I've been collaborating with Baylor Fox Kemper and his group, along with some colleagues of his, such as Ching Li at Los Alamos, to expand wave modeling functionality within CESM. So CESM is one of only two CMIP models that has made wave modeling component a priority. And the collaborative use of NOAA's WaveWatch 3 model has allowed the CESM team to focus on impacts rather than wave model development. And some of these impacts include Langmuir turbulence, Stokes forces in the equations of motion, air sea effects, and wave sea ice effects. However, despite the fact that the wave model is part of the CESM2 release version and CMIP 6, it does not have diagnostics that can be called in a CESM standard manner of comp sets or grids or other features that make it look like other model components. It's a little out of sync still. As different wave grids become important, for example, for sea ice, especially where fine grids come into account and WaveWatch becomes very computationally expensive, there's going to be a need to improve the management of the wave component within CESM. So the team at Brown has been working together with the software engineering group at NCAR and the Ocean Model Working Group to develop a more CESM-friendly WaveWatch and faster alternatives over the last several years, predating my involvement in any of this. Today I'm going to be providing an overview of some of the work related to Langmuir turbulence that the group has done, and to make you aware of some of the new functionality that we hope to make available to the CESM community in the very near future, in the coming month or two. And finally, to get your feedback on these developments and input so that we can make these developments fit the needs of the community better. And Frank, you still have your hand up. I don't know if that's is there a question or just...
No, sorry.
Oh, no, that's okay. I just wanted to make sure I wasn't missing something. All right, let's see. So Langmuir turbulence, which is the area I'm going to be focusing on today, is caused by the interaction between mean flow in the ocean and Stokes drift. Langmuir turbulence has been shown to enhance mixing within the ocean surface boundary layer, and it also contributes to entrainment at the base of that boundary layer, which actually can lend itself to deepening of the mixed layer. Mixing due to Langmuir turbulence has been shown by McWilliams and Sullivan to be able to be parameterized by applying an enhancement factor to the turbulent velocity scale used in a K-profile parameterization, and the equation there is given. The enhancement factor is itself a function of the turbulent Langmuir number, which is a function of the surface friction velocity and the Stokes velocity. In order to calculate the enhancement factor and therefore be able to incorporate it into models, numerical models of the ocean, you need to have two things. You need to have the friction velocity from the ocean and the Stokes velocity from a wave model. Okay. And incidentally, this formulation that was developed by McWilliams and Sullivan was based on the results of large eddy simulation studies. Now, in 2016, Ching Li and his co-workers and colleagues looked to investigate the effects of Langmuir mixing in global climate using CESM. And at that point, they did two things. They added Langmuir mixing into the model through the enhancement factor approach that I just showed you to the K-profile parameterization. And they also added WaveWatch 3 into CESM 1.2 as an active component. That's to provide the Stokes velocity. Now, the component was actually two-way coupled. WaveWatch is two-way coupled to the ocean component, the ocean model component. In this case, it was POP2 with velocity and sea surface temperature and boundary layer thickness being passed from the ocean model to WaveWatch 3. And the turbulent Langmuir number and the Stokes velocity being passed back to the ocean model. And there was one-way coupling between the WaveWatch 3 and the atmospheric and other components to pass along things like velocity at 10 meters, wind velocity at 10 meters, and ice fraction for a couple simulations that they did that included an sea ice component. They also considered, in the course of the study, they considered several different formulations for this enhancement factor to account for things that weren't involved in the original estimate. So things like misalignment between the wind direction and wave direction, before finally ending up on the formulation that you see here, which actually does account for that misalignment. And this will come up again later. So they ran a series, again, this is Li et al. 2016, they ran a series of simulations within CESM where they incorporated the Langmuir mixing, and they did run similar runs at the same time without the Langmuir mixing. And basically what you see is that incorporating the Langmuir mixing improves the predictions, the model predictions, particularly related to mixed layer depth and ventilation of the lower ocean. And you can see that here in the graphics from the paper, where at the top we have the observations of summer mean mixed layer depth. In the middle, we have an example here of the simulation with no Langmuir circulation turned on. And then in the bottom, we have WaveWatch 3 running and the Langmuir circulation turned on. And you can see that with the Langmuir circulation turned on, by incorporating WaveWatch 3 and its input, you have an improvement in the predictions of mixed layer depth, summer mean mixed layer depth. This is just one example. Also improved the winter mean mixed layer depth. But it's particularly pronounced here, and you can see it in the Southern Ocean or high latitudes. It's where the effect is most pronounced relative to the example here with no Langmuir mixing. So the idea here is that while Langmuir mixing is important, it improves the ability of the ocean model to predict parameters like mixed layer depth. But unfortunately, WaveWatch 3 is computationally expensive. It makes the simulations take longer to run. So this led Li to develop, to consider different ways to actually parameterize Langmuir mixing and incorporate it into the models. So in the 2017 paper, Li et al. Considered statistical models that might provide a less computationally intensive alternative to using a fully prognostic wave model coupled into CESM to account for the Langmuir mixing. And they took two different approaches. One is to take a climatological approach where they ran a number of simulations with WaveWatch 3 and developed a climatology for the enhancement factor, the epsilon factor, and then used that to predict Stokes drift and Langmuir circulation. The other approach that they took is to develop an approximation of the enhancement factor based upon empirical wave spectra, so assuming a Phillips spectra for the wave field. And doing that allows you to come up with an approximation, formula for approximation that actually is much more cleanly, quickly solvable than using a prognostical wave model. So the graphics that you see here are just comparisons of the predictions for enhancement factor, so the epsilon factor, the magnitude of the Stokes drift at the surface, and then this, what's that? That's the average Stokes drift through the layer, I think. Not the surface Stokes drift, I mislabeled that, sorry. So that's each of these columns, and then on top you see the data wave, and down here the theory wave approximations to those. And you can see that they do, particularly with the theory wave, does a very good job of reproducing the predictions of this is all compared to the wave watch 3. So you have the data wave and theory wave on the vertical axis, wave watch 3 on the horizontal axis, and the one-to-one line drawn up through the center. And these are scatter plots that are contoured by density. So the 33%, I think it's 33%, are in that interior circle, the yellowish color. So to go into a little more detail, the theory wave implementation that Lee et al. Developed is an approximation of the Stokes drift profile based on empirical wave spectra. And it's basically the complete set of equations that describe it is set over here at the right. But what it boils down to is that in order to predict this enhancement factor, instead of needing Stokes drift from a wave model, a prognostic wave model, you can actually get the Stokes or the enhancement factor from a combination of wind velocity at 10 meters, along with the surface friction velocity and the boundary layer thickness, the boundary layer height, which are all provided within the ocean models, outputs within the ocean models, and makes it so that you can bypass the whole need for a prognostic wave model in this case and save computation time. So the theory wave approach, as you can see here, reproduces much of the effect of Langmuir mixing, but at a fraction of the computational cost. So this is an example, again, summer mean mixed layer depth. It's similar to what I showed before. Here we have the observation in this panel, the control, which has no Langmuir mixing. Down here in the bottom left, we have simulation with the full wave watch 3 prognostic wave model. And over here on the right, we have the theory wave model. And you can see that in both of these cases, theory wave and wave watch 3 both provide an enhanced, a better match to the observations, particularly, again, in this case, for the summer mean mixed layer depth around the Southern Ocean, in the Southern Ocean. In both cases, then it's an improvement over not having Langmuir mixing, and therefore there's some justification here for using this greatly simplified approach, the theory wave approach, rather than the prognostic approach, because of the computational savings. So just to bring you up to date then, so that's the background. Theory waves was, again, developed by Qing Li working with Baylor, Fox Kemper, and others. We're in the process now, or I am in the process of incorporating that fully within CESM as a standalone component. So I'm developing a standalone theory wave component that the idea is that we'll be able to drop it in and use it in place of wave watch 3 to allow you to model and include Langmuir mixing and Langmuir turbulence in your climate models without the computational cost of running wave watch 3. And in addition to allowing for the incorporation of the Langmuir mixing, we'll also be able to add some additional wave-related parameters, wave statistics, for instance, that would allow for some wave climate analysis. These are the CalClip parameters, things like significant wave height and mean wave direction, things like that, a mean wave period. We can also provide the surface layer average Langmuir number, Langmuir enhancement factor, all of these things within the context of this theory waves component, which is, again, computationally less expensive to run, significantly less computationally expensive to run than WaveWatch 3. The hope there being that now people can start using, in a simplified way, incorporating Langmuir mixing into their models, even if that's not the primary focus of the modeling effort itself, to improve, thereby improving the ocean modeling effort. Now, in addition to this theory waves component, which I said is under development, we hope to have be testing within the next couple of weeks, start doing some thorough testing on it. The other thing that we're developing in parallel with this is a diagnostics package for waves. Right now, there is no the standard diagnostics package to use for waves coming out of CESM. So what we've been doing, or what I've been doing, is building a diagnostic package that's consistent with the existing diagnostics packages. For instance, for the ocean, it can be called in the same way and behave in the same way. It's really just built using the existing packages as a template of sorts. And that will be compatible with, ideally, both output from WaveWatch 3 and from Theory Waves. We're going to try to make Theory Waves module output consistent with the WaveWatch 3 output so that we can use them as interchangeably as possible. And this is where I would like some input from the community in terms of what would be useful diagnostics to include, both in terms of the diagnostic package and also in terms of the theory wave output, what beyond the CalClip statistical wave properties and the enhancement factor and things like that, what would be useful wave components to include so that we can make that available to the community. And then the final thing I would love to get your input on is, because I am relatively new to doing this, modeling within the CESM community, is how to move forward with this. How once things are in place and the code is tested and we have a viable system, what's the process for actually getting this into a CESM release in some sort of standard way? And that's all I've got for you today. But thank you.
Thanks, Paul. Great talk. Are there any questions? Okay, I have one. So maybe while other people are waiting to raise their hands.
Sure.
You have a nice match between theory and diagnostic, a nice match between theory and WaveWatch 3. But like on slide 7, I think you have the PDFs. It's not quite perfect. There's room for improvement. Yeah, here in the PDF.
Oh, absolutely, yeah.
And I'm wondering if you have any ideas about sort of what might be the things that would be the crucial things to improve there, if anything, or maybe this is just sort of an inherent thing that you can't get past using the data that's available.
Well, that's a very good question. Unfortunately, I'm just a programmer. So I don't know that I can dive that deeply into the underlying process here. I mean, the theory wave approach itself has accounted for a number of factors, including like directional wave spreading and misalignment between the wind direction and the wave direction. So that's already baked into this. I'm not sure what the next factor is above that, but this is beyond that. But that's a good question that I can bring to Baylor and Ching.
All right.
For input on.
We should move on. There's plenty of other questions here. So just going to go with what's on top. I think Brandon.
Hi, Paul. Great talk. I really enjoyed that. So the question I wanted to ask is related to the use of the theory wave to get wave statistics. I've seen, Ching's very convincing work that it does a nice job providing an enhancement factor for the Langmuir turbulence schemes, but I haven't seen anything that suggests that wave statistics like significant wave height and so forth coming out of it compare well to observation. So I'm just wondering if you guys have done any work like that, if you have any evidence, or Any comments on that?
No,
Thank you.
we haven't done that work. I mean, my understanding is that the approach in terms of, for instance, statistical or a significant wave height is just an empirical relationship that's being used. It's not coming out of the. It's actually, I think, a separate from the theory wave approach itself. It's something that we're just tucking into the theory wave module. But that's a good thing to do, is to go and look at the CalClip, those sorts of CalClip wave statistics, and see if they actually do provide a reasonable comparison to. Yes, I'll be sure to do that.
All right, sounds good. Thanks.
Thanks.
So Bill Large, you had your hand up, but then took it down. Do you still have a question?
Yeah, I wasn't sure we had time.
We do.
But since we do, I mean, Paul, I mean, all the power to you guys for trying to get it so we can use waves in an efficient way. But I wanted to know, you know, if you look at your mixed layer depths in summer, I mean, this whole concoction of enhancement factor must deepen the mixed layer. There's no choice. It must.
Right.
And it still doesn't do it enough by a long ways. So how open are you, and what other wave parameters could we get for people to start figuring out whether there's other ways of doing this? In particular, the surface Langmuir number is a weird thing because it's an average of a wave quantity over a boundary layer depth, and waves and boundary layer depth are not, well, they're not that related, especially if there's swell. So why would you possibly want to integrate over a boundary layer, a fraction of the boundary depth, rather than an e-folding depth or something? So I think there's an awful lot more work. And when we talk about, maybe in the discussion about what else needs to be coming in, it might be room for people to have ideas where they can play with this some more.
Yeah, I agree. I know that the parameterization does not, it explicitly does not include swell.
And it has the surface Langmuir number, which is really critical, and yet that's a funny thing. So maybe the wave community could talk to us about what should be the Stokes part of a Langmuir number. I'm just thinking there's an awful lot more to do, and if you're open to getting more parameters to us to play with, it would be maybe useful.
Absolutely, that's exactly the sort of feedback I'd hope to get.
All right, we're right back on time. And I saw Frank had his hand up, but it went back down. Maybe we can take that at the end if we need to.
Great, thanks.
Yeah, since we're on time, Bill Large is next.
Yeah, well, it's all it takes me a time to get sharing screen. So I'm going to try.
No problem.
Have you got it?
I see it now.
And I'll try go on to, is it there?
Yep.
Okay, except I can't see it all because of these different blowups and things. All right, so I want to talk, oh, I better go back to the beginning. No, I can't, yeah, there I go. So what I want to talk about is some more model development, and ultimately this is to go with waves and reflects the interest I just had in what Paul was talking about. This is work with Gustavo and Alper, like many other studies you saw today. So you can imagine how busy these two guys are. And here's the idea. We are focusing on these vertical mixing tendencies, which I'm writing just as a stress vector, which is minus the momentum flux vector. So that's just the vertical mixing part of the turbulent subgrid scale stress vector. That's the one I'm interested in. And that can be written as both components in the XY of a model component, and in particular MOM6 grid. And it can also be written as the magnitude of the stress and the direction relative to the X direction. And I'm going to start thinking about what does it look like when we think about the stress vector as magnitude and direction rather than components. Because what MOM6 does now is the stress vector is parametrized in this way, where Km is a parameterized eddy viscosity, which is Km, and that has units of length squared over time. And it is constructed and cooked to align with the shear, because both of these directions are the directions of the shear components. So most of the time, and there are some exceptions in MOM6, it's aligned with the shear. And that's basically says the angle between the stress and the shear is 0. In other words, the stress to the x direction and the shear to the x direction are equal. So that's what we do. But down gradient, this down gradient eddy viscosity, I remember back in my turbulence classes that this was only given in analogy to molecular viscosity, which is a property of a fluid. True enough. But eddy viscosity is at best a property of a rather steady and smooth flow. At worst, it's really a catastrophe. So this is dubious. So the question today is, what if the ocean surface boundary layer, and let's restrict ourselves to this, not the interior that Ali was talking about, suppose it's not steady enough for this dubious assumption of down gradient diffusion. Does it matter? And the whole effort here was to try and see whether it mattered. And to set the stage, let's look at some observations that would say that it probably is not a very good assumption to assume it's down gradient. These are shear observations at 15 north and 135 east by Hughes et al. In 2020. And I looked at these, and they're one of the few observations of near surface shear in the wind direction, that's on the top, and the crosswind direction in the bottom. Okay, and what you'll notice now at the surface, there are no observations. But as far as we can tell, the wind, the shear, and the stress vectors are all aligned at the surface. It's wind stress coming in, creates some shear, that's the stress direction. That looks pretty good. But only at 4 meters deep, you see this is really big in the X direction, in the wind direction, and much smaller in the, and negative in the crosswind. So the shear is about 40 degrees to the right of the wind. And that's at 1 p.m. That's here. If we go to 6 p.m., we find that it's shifted over to about 80 degrees. Okay, very big negative and not so positive in the U. All right, so the question then is, of course, what does the stress vector look like? Well, it's very hard to see how a stress vector, which is a correlation of U and W, which is the integral of a covariance spectrum, has only a single scale right at the local direction. That, in other words, how do you get to 80 degrees when stuff's coming in at the surface? There's shear that's not that 80 degrees except at this peak. How the heck can the momentum flux or the stress vector be aligned with the shear? It would only happen like molecular if it's local, or the instabilities that Ali showed, very local. But this is a boundary layer where eddies are filling up the whole of the boundary layer, and in fact come from all over the place. Now, unfortunately, you can't measure the stress vector in the ocean. There is some evidence that the stress and shear are not aligned in the atmosphere, where you have LIDAR observations of that you can get both the stress and the shear vectors, but in the ocean we can't. So if we look at some of these LES that Paul Brown was talking about, this one's at 47 South 140 with Stokes drift. What I'll show you, what I'm showing is the resolved stress in the LES, the current and the shear from the model, the vectors relative to the wind. And sure enough, what you see is this is the actual currents rotate 180 degrees. This is, this is 1 pi or 180 degrees by about 100 meters in this particular case. This shear already rotates by about 90 degrees by less than 10 meters. Very similar to what we saw in those observations, but the stress vector stays much more aligned with the wind. Okay, and so the stress and the shear in this example are not at all alike. So what are we going to do about that? Well, you can see at least that in this case, it was possible to parameterize this angle between the stress and the wind using Lagrangian shear to the surface and local shear. And that's the dashed line, but it's only one case and it's not perfect, especially right near the nearest the surface, but it's much better and much closer aligned than saying that the stress and the shear are aligned. So there's some promise. That's all at that point is. So here's what we do. We try and do a boundary layer flux profile, an alternative to down gradient, where what MOM6 is doing is it takes a velocity vector, it adds an increment for the barotropic and baroclinic accelerations and Coriolis and things, and then it adds this turbulent flux component, and it lines it with the shear vector and finds its magnitude at n+1, so it's implicit. That's what the I is for. So there's an implicit calculation, and the shear to wind is this angle here. Well, there's also an angle of the wind to the x direction here. And what we can do is say, well, the stress vector need not be aligned with the shear. Okay, in particular, it can be arbitrary angle, and we'll have to parameterize that, and then we'll have to give it a magnitude. And once we do that, whereas MOM6 now adds this implicit increment most of the time, this flux profile will add a flux profile increment, which will not be aligned with the shear anymore. So for boundary layer level K, for example, it has a thickness, HK. This increment in the U direction is the magnitude times the angle relative to X, the difference between, the interface above and the interface below, and then this is just dt and the thickness. And you get the same with the meridional component. So you get this difference, or this shear here is due not only to the magnitude, but also the direction changing with depth. So that's the alternative, and that's what we'll try and do. So what we'll have to do is parameterize this magnitude and this angle, the angle by the stress to the wind. Parameterize those two things, plug it in, and you're gone. Well, it's not that simple. There are some wave implementation issues, which have taken me a few months or more to work out because I'm not a MOM6 aficionado, but thanks to GFDL for consultations and help. This is in a waveless for now, 0.25, and I'll get to it later why we're waiting for the wave case that we want to run later. The global stability of such an explicit velocity increments has been an issue. You can't just put that direction anywhere. If you say that you're going to have all the stress aligned with the wind, it goes nuts. So it has to have some rotation and to keep it stable. C-grid is a pain for this kind of thing in MOM6 because the matching at the boundary layer depth and other things requires U on V points and V on U points. So there's interpolations, and that gets to be a problem near boundaries and topography. Single cell channels don't make too much sense to rotate, and there's a channel drag, which upsets things a little bit. You have to work your way through. But the waveless MOM6, and this gets back to some earlier conversations in this working group meeting, it's tuned for down gradient viscosity. It's already been tuned up. So wave effects, such as you heard with from Paul's talk and retuning, we're trying to wait for the wave average Boussinesq equation set to come into MOM6. This is from Brandon Reichel at GFDL, and he is pretty happy with what he has now, and he's passed it on to Alper, and Alper's starting to run some controls because the LES that you're talking about, and Paul mentioned, as you being used for these parameterizations, they typically use the wave average Boussinesq equation set. So when you take parameterizations out of that, you should put them back into the same equation set. And we're not able to do so yet because neither POP nor MOM have the wave average Boussinesq equation set, but we're hoping to get going on that immediately. So what we're doing for now is look for waveless impacts because we're not going to tune. And they can be for better or for worse. I mean, Ian brought this question up yesterday. Things are tuned, so you can put better physics in and get a worse answer, and vice versa, worse physics and a better answer. We're just looking for now impacts to see whether we can pursue this avenue of research or give up on it if it doesn't do anything. So here's how we do the stress to the wind. This is what MOM6 particularly gets at this one particular time step. And you see at 50 degrees, 15 and 3 degrees north, there's a progression of rotation of the stress and the shear, which in this case are both the same, more in an inertial sense as you get higher and higher latitudes. In the south, it's the other way around and you rotate the other direction. This is 55 south, 47 south. What we're going to do with the parameterization, and it all has to match. So it's kind of a very ad hoc thing at the moment based on the LES to some degree, but that's only, we don't have enough information, but you can see what it does. It keeps the direction of the stress much more aligned with the wind than the shear. So you're not letting it rotate so much and you're changing the direction both in the south and in the north. And these excursions as you get close to the boundary layer depth are due to the fact I'm trying to match so there's no jumps in things at the boundary layer depth. So what we're trying to do is parameterize this stress minus the wind from the wind and the local shear in terms of the local shear, the shear from the surface. And with waves, that'll be the Lagrangian shear. But right now we're in waveless, so they're the same. And this is this match at the boundary layer depth. So as far as the magnitude goes, here's some examples. And basically night, in the morning, and in the afternoon. And this is the problem with the stress, implicit stress magnitude, normalized by U star. So it should be 1 at the surface. You can see the diurnal cycle problem. At night, it's pretty linear. In the afternoon, it gets, it remembers what was happening before, and so it has some memory. And in the morning, it hasn't quite caught up with life. And you also see that there's some really issues, and I'm not sure what this is right at the first grid level, first few grid levels. It doesn't go smoothly to U star squared. I'm not sure why. What we're going to do instead is just take this flux profile as the increment for now. That's the simplest thing to do. But because you're changing the direction in time, these things really smooth themselves out. So you can see that is pretty linear. That's what we'll use. This is what happens in the afternoon, and that's what's happened in the morning. So that's what we will be using, though what you see is that the boundary layer depth, in some cases in the morning is deeper, and in some cases it's shallower. Okay, this is the boundary layer depth here. That's shallower than this one. And this one goes from there down to there. So you get both of these interplays depending on how winds and buoyancy fluxes and everything are interacting. There is an option to do a linear flux profile, as this suggests, from the surface to matching at H. And I just haven't got time to show all these results, but that's an option that I've run. So here's some impacts, and this is a pretty surprising one to me. This is just the mean sea surface height from years 10 to 20 averaged from this experiment with just the changing the direction. And what you see is the complete change in increase in the east-west pressure gradient across the Pacific. So this is almost 10 centimeters higher, and this is a few 5 centimeters or so lower. So that is a big global impact issue that I was not expecting. You see similar things in the Atlantic, but it's a smaller basin, so it's not as big, and a similar thing of an increase in the Indian Ocean. So basically the water is piling up here and it's being taken from around the edges and including the Southern Ocean. So these are 10 centimeter a second changes in the sea level height just from changing the orientation of how you put the same stress into the upper ocean and just the boundary layer. So those aren't small signals. And in particular, I'll get back to these 3 places in the Southern Ocean and just keep referencing, you see these big changes of height. The pressure gradients are really changing, height gradients. So this is the SST. Now, there's a big SST difference along the coast of South America. That's almost a degree. Okay, it's less along North America, and there's the old, Africa. Nothing in Benguela. Sorry, Justin, can't do anything there, which he showed us this morning. But it's quite obvious near the coasts, and that's part of this pressure gradient difference. And then you can see a much colder cold tongue extending out. Okay, now in the Southern Ocean, those are those areas again. And what you see is a warming here, cooling there, warming, cooling dipoles, which we'll get back to. So let's find out what that's doing. What is this east-west pressure gradient doing? Well, it should increase the undercurrent, shouldn't it now? That's what drives an undercurrent. So this is the change in the zonal velocity in a section between 140 and 120 east. No, that should be west, I'm pretty sure. It's just, 140 west. And that's a section, and you see a roughly 25% enhancement of the undercurrent at 140 meters. And it's actually a little bit slower towards the surface flow towards the west is slower. So the shear is actually much increased. The shear from here is a lot bigger. Okay, so there's more shear. If we look at the meridional velocity in the same section, what you see is to the north, it's accelerating and there's more velocity and flow to the north, and there's more flow to the south. That means it's more divergent. That in some shape would be met by upwelling somehow, either as Annalena pointed out, cross isopycnal or the undercurrent coming up, and a bigger undercurrent might just be providing the extra water to upwell, but it upwells. If you look at temperature, it's really a surprising signature. Here's that cooling that we saw and would have expected from more upwelling, but the whole of the middle part is warmer. And I did have a look because I couldn't resist, and this is not a bad thing in the MOM6 solution I have. It is typically, this is still too cold, but relative to some obs at least. So, and that's 2 degrees off the equator and close to a degree on it. So it's not trivial, but now it's hotter here and colder there. So the temperature gradient is much reduced. So there's less stratification and more shear. So it's the Richardson number is overall reduced by a fair fraction by both the stratification and the shear. If you look at salinity, and we heard some talk about that compensating, it compensates in a few places, but not in the middle part, not really right here. And there's a little bit of salinity compensation at the, over on here, but not at the surface. Okay, so those are the impacts there. And now I'll look at the deep mixing bands in the Southern Ocean. So this is the September mixed layer depth, and you see these deep mixing bands in the Southern Ocean where the mixing is quite a bit deeper. In fact, it's getting over 500 meters deep in September. And the difference in the experiment, you can see that it's shallower to the north and deeper to the south. So it's shifted those deep mixing bands to the south, and those correspond to exactly those same points that we saw earlier. So that's a big consistent Southern Hemisphere impact that we see. If I look at the boundary layer depths now in the Atlantic and the Pacific and the Indian Oceans, they're not that different from basin to basin, but basically in the winter hemispheres, you deepen or you shallow, okay? And you shallow a lot more in the Southern Hemisphere in the winter. And in the summer, it actually deepens. And in the tropics, it's always deeper. So these are deeper mixed layers, and they're shallower. So you'll also notice in March, in the summer, Southern Hemisphere summer, this also deepens the summer mixed layer depths like Paul was just showing. And that's a good result. But now what he also says is if you start putting wave effects in, it's going to deepen it even more. Okay, and you could really overcook the goose. If you put everything in that deepens, you're going to end up maybe too deep. But that's when this actually putting in the linear fit actually reduces this. So that's when we're going to have to do some more interplay on how various things work, because you can't just keep doing the same thing in isolation. So we can deepen or shallow in different places at different times, all depending on the way that the winds are going with the buoyancy flux, and it's being put in to the direction of the wind more than the shear. So the next steps are to document this protocol and what happens, these waveless MUM6 impacts, at least document what they are so we understand what it does without waves. So then we can take this wave average Boussinesq equation set from Brandon and with WaveWatch, as we heard. And I'm not convinced that I know enough now to know what I need from a theory wave to get this all working, because the wave effects on taking the stress away from the shear is much bigger with waves than without. And that's why I want lots of parameters till we sort this out. We will do the control and legacy runs. The legacy runs are the wave enhancement factors that Ching Li did. Those will be run. Then I guess if the working group agrees that there were some impacts of note, then we would need to put a much better robust implementation with wave effects into MUM6. And I can guarantee you I'm not the person to do that because I don't know how to code these models very well at all. That would be done. And then you could do a gross retuning and the diurnal, right from the diurnal cycle to climate. Now, everybody you've heard today is talking about these tuning issues. So in some sense, that has to be done for all the different developments we've been hearing about from yesterday and today. That should be done in an organized way. So everybody isn't tuning and get it all nice and tuned. And then you put them all together and they all go whacking off again. We've had that happen before. And then we can do an impact assessment on that. So that's all I have for today.
Thanks, Bill. Great talk. We got several questions. I'm going to start with Peter. I think he got his hand up first.
So, Bill, I was unclear whether this was implemented just in the boundary layer or throughout the whole depth.
Just the boundary layer for now, Peter. Yeah. And I think that's probably the only place these I can be really comfortable unless there's more evidence outside the boundary layer of what to do.
Second, what was the impact in the Labrador Sea, where our boundary layers are not very good at all?
Well, it's a function of season, and I averaged over that. Well, but this is MUM6, so I don't think this isn't POP. So they'll have to, I mean, this is why I didn't want to go and say there's improvements or not. But it certainly does change the boundary layer depth but it's over 1,000 meters, I know that. In winter, in March. I'd have to go and I can find the plot for you somewhere. But I think it is dangerous to try and look for improvements because, as I say, there are more than one thing to be done here in the next development cycle.
All right, we're pretty close to on time, so I'm going to take a risk and call on Gokhan and just do one more question here.
Yeah, I mean, Bill, I'm actually, maybe as you are, quite surprised by the impacts. They seem to be quite large. I mean, if you take the sea surface height impacts at face value, we are talking about 15 to 20% of the change. The change is 15 to 20% of the actual sea surface height. So that's huge. And also the undercurrent changes, all that huge, and it's going to come back to, I guess, retuning exercise. But from your experience so far, why do you think the impacts, I mean, they are bigger than some of the parameterizations that we have incorporated over the years. So why do you think that the impacts are so large?
Well, because the assumption of down gradient viscosity is really bad in general. And every model we've done and all the analysis, we've always made that assumption. And there's just no basis for it. So if you don't require that and you allow the surface currents can get a lot bigger because the surface currents aren't being dragged against the shear, they're going to be dragged more with the wind. So the currents are fast and basically the surface currents are, and that's why more water it's hand waving because I haven't done it all, but that's why more water can blow towards the west. That piles up and that gives you your pressure gradient. Okay. And also when those currents are also part of the shear calculation in the mixed layer depth calculation. And that's why it's steeper. There's more shear. So, but again, I could have got the opposite result and probably come up with hand waving arguments why that should have happened. But what I am very surprised at is the magnitude. But you keep blowing more water over for 20 years, you start tipping the, but they're bigger than I would have thought. You're absolutely right.
Yeah.
All right. I don't want to go too much past the schedule here. So Frank, I think if we could hold the question till the end, that'd be helpful. Thanks. So are you here, the next speaker?
Yes, I am.
All right.
All right. Okay. So I'll start. So my name is Hee Wang, and I'm a project scientist of UCAR and hosted by GFDL and stationed in University of Michigan. So today I'm going to present some of our work on the tidal simulations in MUM6. And this is a collaboration between GFDL, U of M, and Florida State. So much of the material that I'm going to present today is still kind of work in progress. And actually some of the results are just a few weeks old. And so any comments and suggestions are more than welcome. Okay. So our overarching goal here is to get better tides in MUM6, which serves to the application of in both forecasting and long time scale climate change studies. And so the information, the improvement that we make should be able to reduce the overall tidal error for both applications. And so for climate change studies, there are two special aspects that we need to take care of. So firstly, because we probably won't be able to run the model in a high resolution, we wanted to have a relatively small accuracy compromise with the low resolution run. And secondly, we want the model to be self-contained, which means that it doesn't really rely on any input based on the current climate. There are many factors that we can consider to make the tide better in the model. Today, I'm going to focus on specifically the resolution of the topography. And if we have time, I'll go back to several other factors here. So the main topic here is to study how subgrid scale topography may help with the tide in low resolution rounds. A few words on the model, on the experiment setup. So we are using a very idealized setting. So the only forcing for the motion model we have here is the M2 component of the tidal potential. And we use a idealized calendar, which means that we don't have to deal with nodal corrections. So the equation here just shows a very simple form of the forcing, which is the semi-diurnal M2 tide. We only use one layer, which makes us really focus on the barotropic tide, and also makes the experiment relatively shorter. So each experiment runs for 20 model days, and we use about 3 days for analysis. And the model, and we use a topographic in linear wave drag to sort of damp the tide. And most of the runs are run in the resolution of about 1/12.5 degree resolution, which is about 0.08. But we also compare results with a higher resolution round, with a 1/25 one. For verifications, so the model, the output sea surface height from the model is firstly calculated into the, we first extract the tidal sea surface height, amplitude, and phase from the harmonic analysis, and then compared it with the TPXO product, which is a satellite altimetry simulation, and you can see the amplitude and the phase of the M2 component of the sea surface height from TPXO in this figure here. So when we do the comparison, we calculate the difference between, we calculate the error between the model of the model on each grid points, and we take a global average and use satymetrics as the satymetric as a sort of how the model is doing with the errors. And the error can, of course, decompose into the contribution from the amplitude and from the phase. So to set up a context of the subgrid scale topography, I'm going to first show here how resolution, especially that of the topography, affects the tidal errors. So the panel on the top shows the tidal error with a 0.08 degree resolution round, and from the left to the right, I'm showing here the total error, the contribution from the amplitude and contribution from the phase. So these 0.08 degree resolution round is actually coarsened from the 1/25 degree resolution data set, and the tidal error for that is shown in the middle panel, and then the lower panel shows the difference between the two, and so blue means that it's better with a higher resolution, and this is not surprising. This is what it should be. But the question here is, is there any way that we can make the low resolution better without really, double the resolution? And so our attempt is to use the subgrid scale topography. This part of the work is built on Alistair Ashcroft's 2013 paper. And as I mentioned, this is still a work in progress. And I'm going to give a brief introduction on the concept, how we implement the idea into MUMP6, and then show some preliminary results on the tidal errors. So for the ocean model, the accuracy of the topography is directly connected to the horizontal resolution. So when the topography is discretized on model grids, there's usually, in most cases, just 1 degree of freedom per grid cell. So increasing resolution, as we see from the previous slide, does give us a better tide, but it can be very costly. So this is especially relevant for climate change studies, in which case we usually couldn't really run it in a high resolution. So the idea of the subgrid scale topography is to incorporate some large scale effects of the topography that is not resolved by the model without really increasing the model's resolution. This includes some constraints we put on into the volume transport across the cells, and as well as the capacity of each cell. So the figure on the right shows us an illustration how this is achieved. So basically, we are translating this very complex subgrid scale topography into the vertical profile, into the simple profile of the depth. And then we can approximate the relative openness at each depth with just the minimum, with the mean, maximum, and the minimum of the subgrid scale topography statistics. So in theory, that we can add more accuracy by adding more parameters, but we'll start with these 3 first. So this statistical description of the subgrid scale topography can be used for both the edges and the centers of the cells, which we will address separately in the next two slides. So porous barrier. So in this case, we address the subgrid scale topography on the edges of the cells. So in the models, we don't really have topography information on the edges of the cells. And when we actually need it, like calculating the transport across the walls of the cells, we interpolate them from the cell center. We can't assume a relatively complicated topography profiles than just a piecewise constant, but it doesn't really add into more information and also assumes a somewhat smooth profile across the cells. So for instance, the continuity equation in MOM6 is sort of simplified as this equation here. And as you can see that there is no explicit dependence of topography in this equation. So the dynamic effect of the topography is really to place and or displace the thickness H, which is down really outside of the continuity equation. The continuity equation itself doesn't really know where the volume is actually located vertically. In the advection scheme that we have here, the thickness is I think it's a upstream biased advection scheme, which is constrained by the flux limiter to ensure monotonicity. And so the porous barrier comes into a modification with the width of the cell instead. This is done by multiplying a weight function to the edge at the edges of the cells. And this part of the code, by the way, which is written by the Princeton US students, Sam Dikovsky, when initially focused more on a localized implementation, and this has already been live in MOM6 repo on JFDL side. And some tricks has been made offline to allow the global implementation shown here. So the idea is basically we can calculate using this weight function from the subgrid scale statistics, we can form a profile and the integral for which will be applied as a weight to each layer. For instance, if the bottom of the layer is higher than the highest point of the topography, then the cell is completely open. If it is below the minimum, then it's completely blocked. Sorry. So similarly, we can specify the depth profile within each grid, at the centers of each grid cell, and use this to constrain the capacity of each layer. So in this case, the interface height, including the surface height, is modified, and this can potentially have an effect on the amplitude error of the tide. So the implementation of the porous media probably will be a little bit different from the porous barrier. We can one way we can do this is just to giving the area in the continuity equation a weight function, or another way to do this is to use the weight function to adjust the final product of H to have a sort of adjusted new interface height. This is still in a concept stage and has yet to be added into the code. So next, I'm going to show some preliminary tests and results really focus on the porous barrier. So the way that we do this is to use the previously mentioned 1/25th degree resolution data set as a kind of our source topography. And so the solution of that will be our targets. In the first set of experiment, which we actually saw just earlier, is to compare the 1/25th and degree resolution result and coordinate it by a factor of 2 without any other change. The second set of experiment, we take the 1/12th degree resolution but added a porous barrier, and the depth parameter for the porous barriers generated from interpolating the 1/25th topography, which only has information on the cells. So it doesn't really go beyond that in terms of accuracy. So this is what we have for the weight functions on the edges with U phase and V phase. So you can see that this is in a way, this is a moderate modification of this. So the number here really shows the percentage of the openness of each walls. One of the things that we are working on is to test the sensitivity of the tide into different locations of these cells, because one would imagine that because of the modification here, so the previously satisfied CFL may be violated in this case, which means we need to shorten the time steps, which really counterfeits the purpose of this approach. So this is just to repeat from the previous slide. What I'm showing here is a comparison between the 1/25th and degree round and the round with the coarsen resolution, and the bottom below shows the difference between these two. So the magic number here is 0.04 centimeters. This is to be compared with the round with the coarser resolution plus porous barrier, because as you can see that the resolution, the error increase by coarsening the topography is much smaller in this case with the help of porous barrier, or put it another way, by adding a porous barrier to the coarser resolution topography, we further reduces the tidal error. We also noticed that the reduction of this error is really is larger for the face. This is consistent with our intuition that it is really the signal propagation that's got improved by the porous barrier. And this also echoes the tsunami travel time test case in Alistair's 2013 paper. So, and we do expect further improvement with the help of porous media. So I think I'm running ahead of my time, so I'm going to show some other efforts that we made to make the tide better in MUM6. So first thing is the self-attraction loading term. So the SAL term basically describes the physical process that is due to the gravitation change induced by the sea surface height change, and also the deformation of the solid earth as a response to that. So the accurate calculation of that involves a fully spheric harmonic decomposition of the global sea surface height field, which is costly and time consuming. So as a compromise, there are other ways to, but this term is really important for the tide. So as a compromise, one way to do this, which is default in most models, is to use the scalar approximation, which means that we multiply the sea surface height by the factor, usually about 10% of that, 10% of the sea surface height, to treat it as a SAL term. And the error of that is shown on the panel on the top. The second approach is to just get the SAL field from, say, the tidal model, and read in as an external input. So it's pretty obvious that the reading tide gives us a better, the reading approach gives us a better tide, because basically we're adding an additional constraint to the model here. But this is not ideal, because we don't really expect the tide and the SAL term to be unchanged in the long run. Especially the SAL term is not really limited to the tide. Actually, it's because it's a function of the sea surface height, so that includes other processes. So the more ideal ways to use a more computationally efficient way to do this online, and this is something that we're exploring. And another thing that we checked is the interaction between the tide and Antarctic ice shelf. So what I'm showing here is two topography with the same resolution, but the only difference, as you can see on the little map on the right, is the topography under the ice shelf in the Antarctic. So the one on the top is without it. The one in the middle is included. So there's a big difference between these two, and also this change is really not local. So which suggests the importance of a proper treatment of the physical process there. One last thing that I'm going to mention is wetting and drying. So this is something that may be useful for the long time scale studies, because so MOM6 can do wetting and drying. I think that's a takeaway message here. And what I'm showing here is the topography near the Hudson Strait, which is one of the largest, which is one of the regions that have the largest tide. So this is just a kind of illustration of how with a tide we can do wetting and drying in this tide experiment. So as you can see that, with M2 tide turned on, that we can have the land flooded and some part of the ocean dried out. And so this is we don't really find a significant change in terms of tidal errors with this with the wetting and drying, but we'd expect this will be a useful feature for the long-term studies. I think I'm about to run out of time. So this is my conclusion slide. So what we just to summarize what I've shown today. So we show some initial results with the porous topography, which looks promising. Of course, there are some further analysis need to be focused on the details in like how do we interpret the interface height into cell edges, as well as how do we what's the best way to get these topography parameter from high resolution data set. And then of course we need to implement the porous media to get a more accurate tide. Inline SL seems to be important, and finally wetting and drying works for MOM6. So I'll stop here and take any questions.
Thanks, really interesting talk. Enjoyed it. We do have time for a couple of questions here before Enrique's talk. Steve Griffiths.
Yeah, thanks for that update. One of the applications with MOM6 that we're interested in is massive changes of mass of the planet when you move ice sheets around, you melt an ice sheet. Is the work that you're doing on the self-attraction and loading going to be something that we could use potentially for, say melting Greenland, and you have a huge change in the geoid, the rotation of the Earth, or is that more work that needs to be done from a geophysics perspective to get more, fingerprint sort of work into it? Or is self-attraction and loading work you're doing sufficient? That's my question.
That's a good question. I never thought about that, but I think from my understanding that the way that we anticipated with the inline self-attraction loading term is just to have a more efficient way of decomposing the sea surface height field into with the spherical harmonics, but it doesn't really include any, say, changes in the geophysical field. So I guess I'm not sure the answer to that.
Okay. It's something to think about, because it would be nice, if you just give it a mass field, mass of the planet, however it's distributed, and than the ocean. You could feed that into the 3D ocean circulation. It's something that nobody has done, but a lot of people have done it offline. I wrote a paper with Bob Kopp 12 years ago, and looking at the fingerprint, sort of the impact of the fingerprint on the circulation is interesting.
Yeah, sure.
It was done offline. It wasn't done interactively. So nobody's done it interactively.
Mm-hmm.
To do more on sea level, it would be nice to get that technology maybe thought about in what you're doing with the SAL.
Mm-hmm. Yeah, actually, one thing that Brian had in my mind, which is something that he's still be interested to do, is to evaluate this geophysical effect, like the Earth is not a sphere, and how do we take it into that consideration to get a better tide, if that actually gives us a better tide by taking that into consideration.
Thanks.
All right, I think we do have time for Frank's question, and then we'll move on to the next speaker.
Okay, this is a little bit off the wall, but quite a few years ago, Steve Jane and I were playing around with using with POP, trying to simulate the low frequency tides, the monthly and fortnightly tides, as a way to assess our representation of topography. I'm wondering if you've, because those tides have dynamics which are closer to the general circulation dynamics that we're interested in as well, but yet we know the answer, what the answer should be for the fortnightly tide. I'm wondering if you've looked at all, or have thought about looking at all at the lower frequency tidal simulations.
No, we haven't really looked at that, but that'll be something we'll be interested in looking into in the future.
All right, thanks again, He. Great talk. Enrique, are you ready? I think I saw the name on the list. Oh, I see you, but don't hear anything.
Yeah, let me okay. Can you see the presentation?
Yes.
Yep. All right. Great. Good afternoon, everybody. So I think last time this group has met, which I think it was about a year or so ago, we had a whole bunch of sessions on MOM6, and in that meeting, I presented some of the philosophy and some of the details of the implementation of the open boundary conditions in MOM6 that we, as we conceived them and implemented them. And I'm not going to repeat that today here. So I think those presentations are online somewhere, and there's a lot of information on GitHub and other places like that. There is a chat question already.
Yeah, we're seeing presenter mode rather than presentation. Is that what you were going for?
No. Okay. Hold on. Let me stop that. Let me stop sharing that and try that again. Ooh, where are we? Where is my presentation now? That disappeared. Okay, give me a second here. I'm gonna let me try that again. How's that? Better?
It's the same to me as it was.
I'm not sure what you're seeing.
Yeah, we still see the presenter mode, but we can certainly read the slides. It's all there.
Okay.
If you just want to go ahead.
Yeah, it's doable.
I'm just going to go on with that.
Yeah, that's good.
That's okay. Yeah. All right. So what basically what I want to do today is just show you where we are with this. So it's a bunch of applications. I'm not going to get into any of particular details of what we're doing. And I mean, the other thing is that when I presented last year, I basically polled everybody that was running any sort of regional application for MOM6. And I try to present a little bit of that. That community has grown significantly in that time. So today I'm going to focus on the things that myself and some of the people that we are working with more closely are doing. And there's, and indeed you're looking at a regional MOM6 high resolution simulation in the North Atlantic here that I will get to a little bit later. The people that are directly involved with what I'm going to talk about today is the crew at GFDL, and I'll highlight, of course, Bob and Alistair and Andrew Ross, who has been working on the West Atlantic as well. And then hopefully I'll get to some of the stuff that Kate is doing up in the Arctic, and Rob Cermak, who's helping us with all of these things, and then the crew in my lab, James, who is a new software engineer, and Dujuan. There are many, many other people. There are now applications that we can keep track, such as the Eastern Tropical Pacific that Scott Backman is doing. There's applications in the Indian Ocean, Gulf of Mexico, tropical Atlantic islands, Great Lakes. So this is a community that's growing quickly. What's driving this is a couple of initiatives, efforts, mostly within NOAA right now. And the first one is the Climate and Fisheries Initiative. And the word initiative in NOAA speak means a big investment, which is making its way through the budget process. And if it survives, the idea is that it will start investing in a nationally integrated coastal ocean modeling and prediction system to support marine resources decisions. So this is bringing together OAR and the Fishery Service and the National Ocean Service to some degree as well. And for that, the idea is that we will develop, or they will develop, or the community will develop some regional high-resolution models in all the coastal areas of the United States. In addition to that, there has been some funding also from the National Weather Service, who has adopted MOM6 as their ocean model. And under that, on a much smaller scale project, I'm funded with Bob and Alistair and Avichal Mehra at NSEP EMC to deliver regional MOM6 capabilities to the National Weather Service for use in their hurricane forecast improvement project, which is part of the hurricane analysis forecasting system that they are working. So these things are some of the early projects that are driving the kind of work that we are doing. So this is where I left it last time. So about a year ago, so whenever that was, we, a few of us, maybe about 3 to 5 years ago, got together and thought that we should try to, we were playing to see whether we could make MOM6 into a regional model. And it was a combination of the global crew at GFDL and then Kate Hedstrom and myself. And, we had more experience with the ROMS model, and we ported a lot of those boundary conditions, or some of those boundary conditions, into MOM6. And we showed this picture, and great, people liked it. And we got the green light to try to develop this into a more robust capability within MOM6. And there's many good reasons why we wanted to do that, not the place here to get into those. But in that picture, it was really just a little bit of eye candy. There was a lot of things that we know we want and need for the to have viable coastal models. And one of the first things that was done, and this is work that Andrew Ross at GFDL, who was I believe a postdoc at the time and is now a permanent member of that community. He has taken the explicit title codes that we had in ROMS and ported them over to MOM6. And here is just simply an example, again, in that Northwest Atlantic domain that you just saw before.
Enrique, I think we're still seeing only slide 1.
Really?
Yes, just click on the on your menu, just click on the left column of slide, just click on slide 5 or 6.
Oh,
yeah, right. That's it. Right.
Right here? Okay.
Yep, thank you.
All right. I will do it this way. Sorry, guys. All right. Did you see any of the previous ones or not?
No, we didn't, but
just
it's okay.
just slide one. That's all right.
That's right. We'll keep going this way. All right. So tides were added to MOM6 explicitly, so we can run them in a regional model, and this is the work that Andrew has done. In addition, as I was saying earlier, there was an interest from fisheries and from the National Marine Fisheries Service in regional capabilities and coastal systems. So doing this with biogeochemistry was a requirement as well. I guess Nikki Zadeh and others, and Charlie Stock and Andrew Ross again, have worked on implementing tracer boundary conditions, open boundary conditions for MOM6 that you see here. And this is now running with the full Cobalt model, which is a 32, soon to be 33 component model. So here, let me make this a little bit bigger. So now regional MOM6 is now running again with explicit tides, biogeochemistry, at least in this domain. I was intrigued by Scott Bachman's talk yesterday. One of the first things that we needed to start understanding in MOM6 is the AL vertical coordinate system and how it is and what impact that has on the circulation. So again, we took this one domain. And by the way, the reason I'm talking about this Northwest Atlantic domain for now is we've had more than a decade of experience in running this with ROMs. So we have some sense of what we like and what we don't like about it. And it's cheap enough that we can do a lot of prototyping in it. So we tried it with two different vertical coordinate systems. And here you see one that's more isopycnal and Z mixed, which is HICOM 1, and then one that's just the Z star coordinate. And you can see on your right what the difference it is. And of course, the difference is pretty significant. And we can't fully attribute it to necessarily the vertical coordinate. There may be issues here that have to do with how the open boundary conditions are being handled in the AL system. And there's some work that remains to be done there. And again, that could be a topic for discussion later. As I mentioned, this domain in the Northwest Atlantic was convenient in many ways to get us going, but we also realized that it's limited. So we have been developing actually three different models in the North Atlantic. The one on the left is courtesy of Chassini and Chu. So same grid that they used for the 2017 paper at 1/12 resolution, which we are now running. And on the right, we have taken a cutout out of that grid. So it's fully collocated within the 1/12 North Atlantic grid. And we are calling that NWA 25, which is a 1/25th version of that, and NWA 1/12 or NWA 12, which is a 1/12th version of the model. So it's basically the same, just with a cutout. And we have tools that we can do this pretty efficiently now. So having this one sort of model that's more comprehensive on like what you see on the left allows us to very quickly take any region that we want and within literally a matter of an hour or two have a new model running anywhere within this particular domain. With an eye towards future online nesting or perhaps even two-way nesting. We are trying to work with grids that are collocated within each other. So some results here on the left, you are seeing the NA12. So this is the 1/12 degree model that goes from about 28 south to something like 78 north. You're looking at sea surface height and you're looking at sea surface temperature on your bottom left. And on your right, you are seeing on the bottom the altimetry eddy kinetic energy. So this is an area that we've been particularly interested in my lab over the years together with Tujuan, Kang. And here is what that model is showing us for the EKE, surface EKE. And there's, it's at this resolution, we understand we have a little bit of an overshoot here, but overall the structure and the magnitude are similar. Sorry, we don't have the same color bar yet, but it's the same range of magnitudes that you're looking at here. Being built with coastal models in mind, here are some a cross section. So I'm showing you here on the bottom right, you are seeing a cross section of temperature across the 72 west longitude. And I was looking in particular, in the last couple of years, we did a few papers on the cold pool over the mid-Atlantic bight. So here you are seeing, if you focus your eyes on the shelf, if you see here the well-mixed winter conditions transitioning in the spring months to a stratified system and forming this cold pool, which even in the Z-star coordinate, we seem to get a very nice representation of that. So we're going to be looking at that. This is a feature that's of particular interest to the fisheries world and the dynamics on the shelf. So it's encouraging that even some of our earlier simulations, we are seeing some of the really nice features that we want. Of course, we recognize the limitations of the 1/12 model. So we have, let's see if this plays or not, maybe. So we have kicked this up to a 1/25 resolution, so about 3 kilometer resolutions for this whole domain. This is run now for about a year. Again, we are, so if we just fix this for a second, we are seeing a better separation in the Gulf Stream. We are seeing some funky stuff here around Charleston Bump that we are going to look into a little bit further. But overall, boundary conditions are working quite nicely, and on we go. So this is, I think, and I hope will become our workhorse coastal or regional model for this part of the world. Just to give you an idea, this model is about a little more points than 1500 by 1500 by 75 square. And on Cheyenne, it's taking us about 40 core hours, 40 and change core hours per day of simulation in here, just for comparison sakes, with a 300-second time step. So we are able to tap into some of the nice features that MOM6 has in order to make the model more efficient. Again, this is looking at the vorticity of that same model, sea surface salinity. You can see, for example, the Amazon plume coming in through the southern boundary here that we have just north of the equator. So we are because of the biogeochemistry interest in understanding the cross-shelf structure of all of oxygen and the carbonate system, we are paying attention to how the rivers are coming in as well. This is a picture from Andrew Ross as well. We are playing with different options in MOM6, and there are many of them. Here you're looking at sea surface height of in both SOTA and GLORIS reanalysis. The base simulation here is what I just showed you for the parameters that were used in the in that NWA 25. And there's things that we like about it. There's things that we think that we can improve. He's played around with changing the horizontal dissipation. But interestingly, here is a different discretization for the Coriolis term that is also showing some differences. So we need to sort of get a little bit more quantitative in understanding what the various options that are available to us. And at this particular resolution, there isn't a lot of experience in the community to know what might work best. This is some of the work that's going on now that we have some models off the ground, so to speak. Okay, so I'm going to spend a couple of minutes just showing you some of the work that Kate Hedstrom is doing up in the Arctic, just to give you a slightly different flavor of what's going on. Of course, this is an area that the sea ice is significantly more important. And this is a model that she has running at 18-kilometer resolution, which is helping her with a prototype. And here is this, I think, is an animation as well. She has added landfast ice that you are looking at here in the top layer, and ice concentration here in the bottom. She is running this. This is running with CIS2. So this is the GFDL CIS model that Hallberg, Bob put together. Any conclusions to date maybe are here. The model does reasonably well, though it seems to overestimate some of the sea ice extent. And she, I believe, is online, and she will be able to answer any questions about this particular effort. So, okay, besides the actual model itself, we have developed a bunch of tools. Regional models are, everybody wants to do their own domain at their own resolution. And for this to be adopted by a larger community, it's important to start working on some of these tools. And this is work that my software engineer and Bob Cermak and Raf Toussaint have contributed, and others are beginning to contribute as well. You can go here, and there is everything from a grid generation package that's interactive, I'll show you in a second, to how to install all of the software, application tutorials, and even example Jupyter notebooks that you can work through and help you set up a model. I think we think that doing this kind of effort for the community will ultimately be really helpful. And here is an example of the grid generation tool. You can fire this up and make a grid to your heart's content. So for my last slide, what I did is I simply took exactly the same slide of my last slide from the meeting, the MOM6 meeting that we had about a year ago. And this is a nice comparison to where we were and where we are and what we need to do. So back then I said the community is rapidly building. I think there's easily more than 50 people attending our every other week meetings to start doing this. So this is catching on rather well. All these imminent developments that we were anticipating at the time, you can put a check mark on all of those. Andrew Ross has added the explicit tides at the boundaries, and Nikki Sadeh and others have worked on the tracer and biogeochemical boundary conditions, and I'll show you an example of that. And at the time, Scott Backman and I think Alper were also working on adding sponge layers for capabilities into the regional MOM6 applications, and I think that's well done now. On the wish list, those are still there, right? So we had two-way nesting and fully embedded in a couple model. I think these are long-term projects, but there's a lot that needs to happen between this imminent developments here in the wish list. And some of that, I think a lot of that has to do with understanding and developing a better intuition for some of the capabilities that MOM6 has. For myself, here I can stop sharing now. For myself, understanding these different vertical coordinates and developing an intuition as to what it is that we should be doing, because the options are really infinite. And I think that Scott's talk yesterday showed that there may be some creative ways to do that. In our case, we also have to keep to be mindful of how those coordinate choices impact the performance of the open boundary conditions. And I don't think that we're quite there yet, but I would say that we're definitely out of the gate and running with this capability, and we look forward to growing it. So I'll end there and happy to take questions.
Thanks, Enrique.
Sorry for the mess up with my keynote. I don't know what happened, but
anyway. Sorry we didn't catch that earlier, and thanks to Alistair for catching it. So I propose that we go till 10 after the hour with questions for Enrique at the most, and then after that we'll have an open discussion. So anything, all right, I've got something in the chat. So thanks, Enrique, says Melissa. I may have missed this. Is there currently a capability for point sources, as in ROMs, horizontal momentum transport, volume vertical flux?
Point sources. So are you
I guess I was thinking, for example, like
river
I may have
inputs?
missed this, but river point sources and things like that.
Yes, you can have mass. You can use a mass source as a river input, and yeah, Bob can nod to agree with that.
All right, anyone else? Okay. Well, I think in that case, maybe we should open it up now for the general discussion, and we'll be only slightly behind schedule instead of waiting all the way till 10 after. So from now till we adjourn at 30 minutes after the hour, we've got follow-up questions for other talks throughout, and then just open discussion. So Frank, go ahead.
Yeah, I had a question for Bill Large, still here. Yeah. So Bill, I was trying to think about, and couldn't do the algebra in my head, with the change in the change in the rotation of the stress relative to the shear. Should we expect a difference in what we would normally call Ekman transport or Ekman pumping? Is the divergence of the geostrophic wind-driven transport do we expect it to be different? And is there a rule of thumb we could look to just based on the, the functions that go into the parameterization?
I'm not surprised you asked that because you brought it up before and I haven't looked at it. I mean, I think the total Ekman transport has to stay the same. But the distribution in the vertical could change. Because don't forget, the Ekman transport in the ocean has to be equal and opposite that of the atmosphere, correct?
Yeah.
So the total transport, I think, can't change, but the distribution could, and therefore the properties it takes with it could. But I don't, that's as far as I've thought on that.
Yeah. Well, I'm just thinking, as we approach the equator, the stress is no longer bounced by the Coriolis force. The zonal stress on the equator is bounced by the zonal pressure gradient. And that's generally what people use to scale the east-west sea surface height gradient, is to say, well, this, and observationally that works pretty well. Just looking at an altimeter and a scatterometer, they balance not just in the zonal, in the zonal gross bulk sense, but fairly locally in longitude. And so I'm trying to understand how this rotation might change that, or at either on the equator or as you move away from the equator, and how that would play into the equatorial dynamics.
What I found is there is a huge break point at about, you can see the trades versus you can see a whole difference in the response with the trades in the westerlies. But as you get closer, I would say around 5 degrees north and south, there's another break point. And what we don't have is any guidance on how to rotate. And what we're doing, I mean, I still have a hard time feeling that the wind there's typically, if you're far enough towards the east, there's a southerly component to the winds. And the pressure gradient is giving you most of the shear. And so that you could, that's where the momentum automatically goes, is with the shear. When the wind's blowing, I doubt it. But how much, what we should really do, given that I don't have a wave LES to do there, I just don't, I don't really know. I do understand, I think, or at least as I told Gokhan, hand wave on why there's more transport across in what I did. Whether it's the right thing to do is quite a different question. And I do think the impacts will be bigger when we put waves in, but they could actually just cancel. So until these different equation sets and the wave parameterizations go in. But I think I don't know what to do with the equator. It's a bit flaky. I mean, it's just no evidence, but there's certainly no evidence to say that the stress should go with the shear.
Okay. Then I guess, I guess just to prompt discussion, people still have the energy for it. I think anyone today who said we can talk about this later, now is later. So, so this is your time to bring that point back up and see what kind of discussion might result.
Bob Hallberg, you had your hand up. There it is.
Yeah. So I had another follow-up question for Bill. So when you're putting the stress in it with a different vertical profile, the work that the wind is doing is the dot product of the stress where it's realized with the velocities. Have you looked at diagnostics of the wind work? And for this, Ian's postdoc Nora Lewis has done some really nice work on the energetics with this model and some nice cleaner diagnostics than we had before. So, but have you looked at the wind work being done with the new formulation and whether it's putting more energy in by this formal metric?
The quick answer is you've seen everything I've seen now. This has only been done for a week or so. And so, in fact, it was Monday that Gustavo ran the diagnostics. So the answer is no. But it is true in all of these cases, and I think that the stress at the surface, everything's aligned. I mean, the wind actually goes into the mean currents first, right? That's what you're doing, and then it's the turbulence that will then either mix and go to potential energy or it'll dissipate. So no, I haven't, but that's a pretty good approximation that things are aligned. And it does seem like all the models are doing that correctly. That's where the shear develops. So right near the surface, that's why you can't keep it in the wind direction. And, or else things go really nuts. So no, I haven't looked, but I would also like to have a much better and more robust implementation before sending anybody off to do anything. Because the first thing was, will this do something? And it seems to do something. But you need to be involved, I hope, in how we actually do this if we really want to get serious.
I can be involved, although I've been having conversations with the people who supervise me about how many things I'm involved with. But this seems like an interesting and important one.
You being GFDL in general, or somebody who knows something about MOM. Okay.
Well, I personally can get involved. I just can't commit to a huge amount of time, but I can provide hopefully useful guidance because you've got now a pretty strong cohort of folks at NCAR who have demonstrated they know their way around as well. So I think we're actually in good shape.
Quickly, I was just going to say Nora would have been here, but she's presenting at the AMS meeting today. But if you wanted to talk to her another time, we could set that up. Keith, you have your hand up.
Yeah, this is a question for Steve Yeager, related to Nikki's question about the difference between the high-res decadal prediction runs in the DPLE. My recollection is that DPLE was the ocean was initialized from core forced Fosse, and I think you said in your talk that the high-res runs were initialized with JRA forced Fosse, and my recollection is that core has anomalous pressure drift in the Southern Ocean, and I'm wondering if that could be playing a role in addition to the resolution differences. But I'm not sure if I'm remembering properly the initializations.
Yeah, DPLE used core 1 that was modified to have a different wind stress forcing in the tropics. So we identified this spurious trend in the wind stress strength, or the easterlies in the NCEP winds that go into core 1. So we swap those out. And yes, high-res DP uses JRA GOGO, DO. But I don't think that that's related to Southern Ocean skill differences. That difference in forcing used in the initialization.
Okay. Okay.
Bill, go ahead.
Can I ask Steve Yeager a question? I want to make sure I got this right. You, at one point you did what you called an ensemble size adjustment, correct?
Yes.
And you got something, but actually, of course, in some sense, practically, you'd actually, need to do the same computing cost adjustment, and that wouldn't be near the same. But when you did the adjustment, it didn't change your results according to what one of the metrics, the RC metric, didn't change. I mean, that stayed as an improvement regardless of whether you adapted or not. Was that the right recollection? I got it written down here if I can find the right metric. One of them didn't need this ensemble size adjustment in order to show the improvement of the high res. And you remember the metric that was? Began with an R, I think.
The RPC.
Yeah, that's it. That was robust no matter on the ensemble size. Is that correct?
I don't quite understand the question. So I showed, this was the final plot that I showed. And I'm comparing the RPC, which is the ratio of predictable components from the DPLE 40 member system to the high-res DP 10 member system. Okay.
Yes, and the high does better.
Yes.
Even though it's a smaller ensemble.
Yeah. So
that was what I thought. Yeah.
This is getting a bit nuanced. I mean, as I mentioned, we want RPCs near 1. We can see that high-res achieves that over most of the regions where skill is high. So that's desirable. With DPLE, you can achieve high skill if you increase the ensemble size to 40. That's shown up here. But it comes at the cost. It comes at the cost of an RPC that is unrealistic. And so this is just another way of seeing the signal to noise issue that exists in these coarse resolution systems. You can throw as many ensemble members as you want, and you'll gradually increase the skill, but you will have an RPC ratio that indicates that the real world is much more predictable than your model itself.
Yeah, that's my interpretation, and that had to do with this the paradox you were talking about. It looks like the high res is a real advance in that. Is that consistent?
That's correct. Yeah.
Okay.
Maybe I'll just follow up with a specific thing and then offer a broad, pose a question to the group. Paul Hall was sort of ended his talk asking, well, what does he do next? Is Paul still on? In terms of bringing the, it looks like he may have dropped off. Oh, no, I see him. In terms of bringing in the theory wave as a CESM component model in the standard distribution, And the answer is that, we have software and science liaisons who can work with you to do that, with the understanding that that's a very small portal into our capability. We have very limited human resources to do that, but those are your points of contact. The co-chairs, myself and Ian, and the software and science liaisons were Gustavo and Alper. And all of our names and emails are on the working group webpage. So that's sort of the pathway. And then there's an expectation that the work will have been done to validate and vet the code to make sure that it meets the software engineering and science standards that we would like to see for something that we're going to then redistribute. So we can iterate with you on what steps would be sensible to achieve that level of vetting.
Thanks. That would be great. Does the same apply for the diagnostics routines? Is it the same process for that as for the model components?
Yeah. Although something else I wanted to bring up, and that is our entire diagnostics infrastructure is undergoing a radical transformation to Python-based scripts. And again, I think talking to people, there is an activity within CGD that's advancing that quite rapidly, called the Earth System, ESDS, I think it's Earth System Data Science. And there's a very active Zulip discussion group that covers that work. And again, I think talking with Gustavo or some of the people involved in that would be a way to get started.
Great, thanks.
Yeah. So then on the point of bringing in new things and tuning the models, this has come up, we are about to launch into bringing, this, as Gustavo is showing, we're launching into starting to do coupled runs and trying to begin the process of developing CESM3, which will involve tuning and choosing the sets of parameterizations we're going to use and tuning those to work well together. And that is, of course, very messy and, at least in my experience, has been a pretty unstructured process. The process going up into CSM2, I think, involves something like 200 full-blown, fully coupled climate experiments, which was kind of a random walk through parameter space of the full complexity of the model. So if people have, and then I guess the thing that's a little bit different for us this time is that we are working within a broader ocean model community. I mean, up till CSM2 was POP, and we were pretty much the POP world, this working group. But now, we have both contributions and experience being developed in other coupled climate systems and data and state estimation systems, regional models. And I think that, potentially enriches our capability, but also can make things more confusing going forward. So I'm sort of interested to hear if people have thoughts on, how we both maintain model diversity going forward, but at the same time learn from each other, and perhaps ways that we might make all of our tuning and development exercises a little more efficient in the coming years. If I get any reaction to that. Bill.
Yes, reaction. This has been a great meeting, but and I know you wanted to talk about the horizontal resolution, but those grid sensitivities really open up another huge can of worms. And it's very exciting, but boy, is it going to make things very, very difficult to know what you've done in one component if that, or in one part of the model, and then that grid comes in and changes and everything goes another way. So how you're going to deal with that, I have no idea. But it seems to me that there needs to be, for what we're after, sort of the next CSM3 components, they don't have to be everybody working on it, but there has to be some kind of schedule when some decisions are made. And otherwise, you're going to be operating in a changing world underneath you. And that one, that really looks promising. That's the problem. But it's pretty, and if Scott's around, he'd probably say it's still not very mature. He hasn't been at it that long, and yet it's something. Anyway, some kind of times when when it's known when we'll have a horizontal grid that's the workhorse, and now a vertical grid, not only resolution but type. So that's those two, the grids are pretty key here, and everything's built on them. So that's a reaction to what you said.
Yeah, I mean, I think that was kind of the trajectory we were on, in a small way with, we had brought our Z-star and hybrid forced models up to a state that, we were moderately happy with, and we're beginning to evaluate tracers and things like that. And then sort of held up waiting to get them going in a coupled system. So now we're back running again, hopefully. In a fully coupled system, would be able to advance that. So I concur that we need to narrow our choices on that fundamental question early. Bob?
So one question with the strategy is whether there will be a hierarchy of different resolutions, both of the atmosphere and the ocean. And one of the things we heard today from he, I think, is an interesting one. As we go to higher resolutions, there are two things that happen. Of course, we resolve the eddies better, but then the other thing is we resolve the topography better in the channels. And one of the things that I'm really excited about with the stuff that Sam Didkovsky and that he showed today is that we have a very real prospect of having different resolutions able to represent the topography much more similar than we had been able to do traditionally. And that's always been one of the big sources of differences when you compare across resolutions, which channels are open, which ones are blocked, are they blocked at different depths? So that part, at least, building on Elster's work from 7 years or 9 years ago now, might offer a somewhat happier outcome if we're trying to consider having the simultaneous development at a variety of different resolutions, with them being able to cross-inform a bit better than they've maybe been able to do in the past.
Yeah, well, to address the question you started with, I think there's certainly an ambition to have a hierarchy of resolutions available. And, with the breadth of interest across the CESM community, it's almost certain that we require more than one resolution to address all of those interests. It's just a matter of how we proceed towards achieving that.
And Frank, that's mixing different resolution atmospheres with different resolutions. So a dense matrix of coupling, or a sparse matrix of high, low, low, and.
Yeah, really, it would be difficult for me to say at this time. I mean, I think we don't want, well, historically, CSM is not supported more than less than 5 standard configurations as, fully vetted, scientifically supported solutions that we will provide a model and a spun up reference case, et cetera. We might provide function, what we would call functional capability, where someone could try this with the parts we provide, but it may not be as scientifically vetted as one of the reference cases. So, That's of course the objective of all of the infrastructure that's been built to be able to mix and match component models across the interface. Well, we're beyond the time we said we would adjourn. Anyone else have thoughts they would like to put to the group before we close for today? Okay. All right. And I guess we'll call it a day and reconvene for another half-day session tomorrow morning at 9:15 Mountain. And I hope to see everybody back then. See you later.